somewhere between Mars and Jupiter, drifting through the cold silence of interplanetary space. There is a world that should not exist. It is not a planet. It is not a moon. It is a battered, scarred, ancient remnant of something that almost became a planet and then had that future torn away from it in a collision so violent that pieces of its body rained down on Earth for billions of years. Its name is Vesta, and almost nobody talks about it. Vesta is roughly 326 miles across. That is about the distance from Los Angeles to Phoenix. You could drive across the entire diameter of this world in 5 or 6 hours at highway speed. Assuming you had a road, an atmosphere, and the ability to survive temperatures that swing between negative 150 degrees Fahrenheit in shadow and 350 degrees Fahrenheit in direct sunlight. And yet, despite being small enough to fit inside the state of Arizona, Vesta has a molten iron core. It has a layered interior with a mantle and a crust, just like Earth. It has mountains, taller than anything on our planet. It has a crater so enormous that it stretches across nearly the entire southern hemisphere, a wound so deep it exposed the world's inner layers to open space. And it has been sitting there, silently, for 4.5 billion years, carrying secrets from the very birth of our solar system that we are only now beginning to decode. Here is the part that should unsettle you. Scientists have found pieces of Vesta on Earth, not metaphorically, literally. Chunks of rock that were blasted off Vesta's surface by ancient impacts have traveled across hundreds of millions of miles of empty space, entered our atmosphere as fireballs, and landed on our planet's surface. We have picked up these fragments with our hands. We have carried them into sterile laboratories, sliced them open with diamond saws, and matched their chemistry to the surface of a world that orbits more than 100 million miles from here at its closest approach. Those fragments told us something that overturned decades of assumptions. Vesta is not just an asteroid, it is a frozen embryo, a protoplanet, a world that began the process of becoming a full-sized planet, like Earth or Mars, completed the early stages of that process, and then stopped, frozen in time, suspended in an incomplete state of creation, like a clock that was wound but never allowed to tick. Think about what that means. Every planet in our solar system, Earth, Mars, Jupiter, Saturn, all of them, started as something like Vesta. They were small, hot, molten bodies that collided and merged and grew over millions of years until they reached the sizes we know today. Vesta began that same journey. It melted. Its interior differentiated, separating into distinct chemical layers. Its heavy metals, mostly iron and nickel, sank to the center under the pull of gravity, forming a dense metallic core. Its lighter silicate rocks floated upward, separating into a rocky mantle and a thin basaltic crust. Vesta was doing everything right. It was following the planetary playbook step by step. And then Jupiter happened, the gravitational bully of our solar system, a world so massive that it contains more material than all the other planets combined, stirred the asteroid belt into chaos, accelerating the relative speeds of the small bodies within it, turning gentle mergers into violent, shattering collisions. Vesta and its neighbors were prevented from ever combining into a full planet. Vesta was stranded, left behind, abandoned in a cosmic construction zone that would never be completed. A world that was born but never allowed to grow up. And the violence did not end there. Over the next 4.5 billion years, Vesta was pummeled by impact after impact after impact. Most were small, the routine bombardment that every body in the solar system endures over deep time. But at least 2 of those collisions were so catastrophic that they should have shattered Vesta into fragments. One of them carved out a crater nearly as wide as Vesta itself. A hole so deep it exposed the layers beneath the crust, ripping through the geological record like a knife through sediment. Billions of tons of material were blasted into space, forming a swarm of smaller asteroids that still trace Vesta's orbit around the Sun today. Some of those fragments drifted inward over millions of years, nudged by Jupiter's gravitational influence, crossing the orbit of Mars, crossing the orbit of Earth, and eventually falling through our atmosphere as meteorites. And yet, through all of that destruction, through billions of years of bombardment, through at least 2 impacts that should have been fatal, Vesta survived. Battered, scarred, diminished, missing perhaps 1/10 of its original mass, but intact, its iron core still held, its layered structure still persisted, it refused to die. By the end of tonight, you are going to understand what Vesta truly is. Not just a lump of rock drifting between planets, but a time capsule from the most violent era in our solar system's history. You are going to learn how a single space mission revealed that this tiny world has geology as complex as Mars. You are going to discover why the scars on Vesta's surface tell a story of destruction so extreme that it reshaped the entire inner solar system, sending fragments raining across the orbits of every rocky planet. And you are going to confront a question that scientists are still wrestling with today. How did something this small, this fragile, this exposed to the full fury of billions of years of cosmic bombardment, manage to survive at all? The answer, it turns out, reveals something profound, not just about Vesta, but about the fundamental process by which worlds are born and destroyed. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. Now, let us begin. To understand what makes Vesta extraordinary, we first need to understand the place where it lives, and why that place exists at all. The asteroid belt is one of the most misunderstood regions in our solar system. Movies and television have trained generations of viewers to imagine it as a dense, chaotic field of tumbling boulders, a gauntlet of spinning rocks that any spacecraft would need to dodge and weave through to survive. The image is vivid, dramatic, and almost entirely wrong. The reality is that the asteroid belt is overwhelmingly empty. If you were to stand on one asteroid and look around, the nearest neighboring asteroid would typically be millions of miles away, so far that you could not see it with the naked eye, even if you had perfect vision and all the time in the world to search. The total mass of every single object in the asteroid belt, every rock, every pebble, every grain of dust, every boulder, every minor planet, adds up to roughly 4% of the mass of our moon. 4%. Our moon is itself a small body compared to the planets, and the entire asteroid belt is a rounding error compared even to that. If you gathered every asteroid into a single ball, the result would be a body far smaller than Earth's moon, roughly 600 miles across, less than a third the moon's diameter. The asteroid belt is not a crowded highway of destruction. It is a vast quiet desert, punctuated by a few widely scattered stones, each one alone in an ocean of emptiness. But it was not always this way. And that is where Vesta's story truly begins. 4.5 billion years ago, the solar system was young. Our sun had recently ignited, burning through hydrogen with the fierce intensity of a newborn star, pouring light and heat into the vast disk of gas and dust that surrounded it. This disk, the solar nebula, extended billions of miles from the sun in every direction, a flat, rotating pancake of raw material waiting to be built into worlds. And within it, a process was already underway that would transform formless dust into everything we know today. It started with grains, microscopic particles of silicate and iron drifting through the gas, bumping into each other and sticking together through weak electrostatic forces. Grain by grain, they built into clumps. Clumps grew into pebbles. Pebbles settled toward the midplane of the disk and accumulated into rocks. Rocks crashed together to form boulders. And boulders, drawn by the faint pull of their own gravity, merged into larger and larger objects until they reached kilometer scale and beyond. Scientists call these early bodies planetesimals, the building blocks of planets, each one a rough, irregular mass of primordial material, heated by the friction of its own formation and the decay of short-lived radioactive elements trapped in its rock. This process, accretion, was happening everywhere in the disk simultaneously, closer to the sun, where temperatures were high enough to vaporize water and other volatile compounds. Only rock and metal could survive in solid form. The planetesimals in this region were dense but small, made entirely of refractory materials. They collided and merged over millions of years, building the 4 terrestrial planets one impact at a time: Mercury, Venus, Earth, Mars. Each one was assembled from countless smaller bodies, each collision adding mass, each merger bringing the growing planet closer to its final size. Farther from the sun, beyond a boundary called the frost line, located at roughly 2.7 astronomical units from the sun, Near the present-day outer edge of the asteroid belt, temperatures dropped low enough for water to freeze into solid ice. This was transformative. Ice was abundant in the solar nebula, far more abundant than rock alone. Planetesimals that formed beyond the frost line could incorporate water ice along with rock and metal, making them substantially more massive than their inner system counterparts. These larger bodies grew faster, their enhanced gravity pulling in material from a wider region of the disk. In the outer solar system, the largest of these icy planetesimals grew massive enough, perhaps 10 to 20 Earth masses, to begin capturing the surrounding hydrogen and helium gas, building the enormous atmospheres that characterize the gas giants, Jupiter, Saturn, Uranus, Neptune. Each one began as a rocky icy core that grew large enough to sweep up gas from the nebula before the nebula dissipated. The region between Mars and Jupiter was caught in the middle of this grand construction project. It sat at a critical boundary, close enough to the Sun that its planetesimals were rocky, but far enough out that there was ample material for growth. By all expectations, this region should have produced a planet. The mathematical relationship, known as the Titius-Bode law, which described the spacing between known planetary orbits with startling accuracy, predicted a planet in the gap between Mars and Jupiter. In the late 18th century, a group of astronomers calling themselves the Celestial Police organized a systematic search for this missing world. They were certain it existed. The math demanded it. Nature, they believed, did not leave gaps. But nature had other plans, and those plans were dictated by Jupiter. Jupiter did not merely grow large, it grew large fast. Current models suggest that Jupiter's core reached a critical mass, roughly 10 times the mass of Earth, within the first 3 to 5 million years of the solar system's existence. At that point, runaway gas accretion took over. Jupiter ballooned from a large protoplanet into a gas giant colossus in perhaps as little as 100,000 years, a geological eye blink. When the process was complete, Jupiter held 318 times the mass of Earth, with a gravitational field so powerful it could reach across millions of miles of space and reshape the orbits of anything in its neighborhood. For the asteroid belt, Jupiter's early formation was catastrophic. As Jupiter's mass grew, its gravitational influence penetrated the belt, stirring the orbits of the planetesimals within it. Objects that had been orbiting the Sun in relatively circular, coplanar paths were tugged into more elliptical, more inclined orbits. Their relative speeds increased. Collisions that had once been gentle, slow enough for objects to stick together and grow, became violent and destructive. Instead of merging, planetesimals began shattering each other. Instead of accretion, there was erosion. The planet-building process went into reverse. Jupiter also created gravitational resonances within the belt, specific orbital distances where its periodic gravitational tug was amplified, pumping energy into any body unfortunate enough to orbit there. Objects in these resonance zones had their orbits destabilized, sending them careening into the inner solar system or flinging them outward toward Jupiter itself. Over millions of years, these resonances carved gaps in the asteroid belt, the so-called Kirkwood gaps, named after the 19th century astronomer Daniel Kirkwood, who first identified them. Depleted zones where few asteroids survive because Jupiter's gravity ejects anything that drifts into them. The result was a massacre. The region between Mars and Jupiter, which may have initially contained enough material to build a Mars-sized or even Earth-sized planet, was ground down, scattered, and depleted until less than 1,000th of its original mass remained. The planet that should have formed was never given the chance. Jupiter killed it before it could be born. And yet, a few survivors clung to existence. In the rubble of that unfinished world, a handful of bodies had grown large enough and strong enough to withstand the new regime of high-speed impacts. The largest was Ceres, roughly 600 miles across, massive enough to have pulled itself into a roughly spherical shape under its own gravity. Ceres is classified as a dwarf planet, the only one in the inner solar system, and it carries its own mysteries. Its surface is scarred by craters and adorned with bright spots of sodium carbonate, evidence of briny water that once percolated through its interior and reached the surface. Ceres may still harbour a layer of liquid water beneath its crust today, making it one of the most intriguing targets in the search for environments that could support life. But the second largest survivor is the one that concerns us tonight, Vesta. And Vesta's survival is far more surprising than that of Ceres, because Vesta did something that Ceres apparently did not. It fully differentiated. It melted all the way through. Its interior separated into distinct chemical and physical layers, each one arranged by density, exactly as happens inside a terrestrial planet. Vesta became a miniature world, complete with an iron core, a silicate mantle, and a basaltic crust. And the fact that we know this, that we can describe Vesta's interior structure with any confidence at all, is one of the most extraordinary detective stories in the history of planetary science. It is worth pausing to appreciate the scale of what Jupiter accomplished, or rather, what it prevented. Simulations of solar system formation suggest that the region between Mars and Jupiter once contained enough solid material to build a body several times the mass of Mars, perhaps even a body approaching the mass of Earth. Had that material been allowed to accrete undisturbed, the solar system would contain not 4 terrestrial planets but 5. There would be a rocky world between Mars and Jupiter, a world with its own atmosphere, its own geology, potentially its own conditions for habitability. Instead, that world was never born. Its raw materials were scattered, ground down, and lost, and all that remains of its potential existence is a sparse collection of surviving fragments, the asteroid belt, haunted by the gravitational ghost of the planet that prevented its birth. Understanding this context is essential to understanding why Vesta matters. Vesta is not merely a survivor of the asteroid belt. It is a survivor of the planet that should have been. It is a fragment of an unborn world, the largest surviving piece of a construction project that was demolished before completion. And unlike most fragments, which are cold, undifferentiated, geologically inert chunks of primitive material, Vesta completed the first and most fundamental step of planetary formation. It melted. It organized itself. It built the architecture of a planet inside a body too small to ever become one. The story of Vesta's discovery begins on the evening of March 29, 1807, in the city of Bremen, in what is now northern Germany. Heinrich Wilhelm Olbers, a physician by day and an astronomer by night, was scanning the sky with his personal telescope. Olbers was already a figure of some renown in the astronomical world. 5 years earlier, he had discovered Pallas, the third asteroid ever identified. The very concept of asteroids was still startlingly new. Ceres had been discovered in 1801 by Giuseppe Piazzi, an Italian astronomer who initially thought he had found a comet. Pallas followed in 1802 and Juno in 1804. Each new discovery deepened the mystery of the gap between Mars and Jupiter. Instead of the expected planet, astronomers were finding small, faint wandering points of light, bodies clearly orbiting the Sun but far too small to be planets. Were they fragments of an ancient world that had shattered? Were they debris from a collision between two larger bodies? Or were they something else? Survivors of a process that had gone wrong. On that March evening, Olbers noticed a faint point of light that had shifted position relative to the background stars. He tracked it over several nights, plotted its motion, calculated a preliminary orbit, and confirmed that it was a new member of the growing family of bodies orbiting between Mars and Jupiter. He named it Vesta, after the Roman goddess of the hearth, home and family, a quiet domestic deity, the keeper of the sacred flame that burned at the center of Roman spiritual life. The name was chosen for beauty, not for significance. Olbers could not have known that the object he had just discovered was not merely another fragment of rubble, but a frozen embryo of a world, carrying within it the thermal and chemical memory of the solar system's infancy. For the next century and a half, Vesta was treated as just another asteroid, one entry in a growing catalogue of thousands. Astronomers measured its orbit with increasing precision. They noted its period, 3.63 years to circle the Sun. They measured its distance, an average of 2.4 astronomical units from the Sun, placing it firmly in the middle of the main asteroid belt. And they consistently noted one feature that distinguished Vesta from almost every other asteroid: its brightness. Vesta shines. Not like a star, of course, but for an asteroid, it is remarkably luminous. Its surface reflects roughly 42% of the sunlight that strikes it, a measurement called albedo. making it one of the most reflective, solid bodies in the entire solar system. For comparison, our moon reflects only about 12% of the light that falls on it. The average asteroid reflects roughly 7 to 15%. Ceres reflects about 9%. Vesta's albedo is nearly 4 times higher than the moon's and 3 to 5 times higher than the average asteroid's. Under ideal conditions, dark sky, no light pollution, knowing exactly where to look, Vesta can actually be seen with the naked eye from Earth. It hovers at the very edge of human visual perception, a faint speck of light drifting slowly against the backdrop of stars, a world hiding in plain sight. That unusual brightness was the first physical clue that Vesta's surface was not typical. Dark, carbon-rich asteroids, the most common type, absorb most of the sunlight that hits them, appearing nearly black. Vesta's high reflectivity suggested a surface made of something fundamentally different. Fresh, bright, mineral-rich rock, more similar to the volcanic surfaces of the moon, or the young lava flows of Earth, than to the ancient primitive material found on most asteroids. The significance of this clue would not be fully understood until the 20th century, when advances in spectroscopy gave astronomers the ability to decode the chemical signatures hidden in reflected light. And when they turned that tool toward Vesta, the result would transform our understanding of the asteroid belt forever. Throughout the 1900s, scientists studying meteorites, those fragments of solar system material that survive the fiery plunge through Earth's atmosphere and land on the surface, noticed a persistent anomaly. Among the thousands of meteorites recovered from deserts, ice fields, and farmland across the globe, there existed a peculiar family that refused to fit neatly into the standard classification scheme. They were called head meteorites, an acronym derived from the names of the 3 subtypes within the family: Howardites, Eucrits, and Diogenites. What made head meteorites distinctive was their unmistakably igneous nature. Unlike the majority of meteorites, which are chondrites, ancient, unmelted mixtures of minerals, metal grains, and tiny spherical structures called chondrules that have remained essentially unchanged since the solar nebula condensed. H-head meteorites were volcanic rocks. They had formed from magma. Eucrits resembled basalt, the same dark, fine-grained volcanic rock that paves Earth's ocean floors and blankets the vast lunar maria, those dark plains visible on the moon's face. Diogenites were coarser-grained, rich in the mineral pyroxene, resembling rocks pulled from deep within a planet's mantle. Howardites were breccias, tumbled mixtures of eucrite and diogenite fragments, cemented together by the shock and heat of impact events, as if someone had taken pieces of a world's surface and pieces of its interior and blended them into a single chaotic sample. The chemistry of these meteorites told an unambiguous story. They came from a body that had once been completely molten, a world hot enough to melt rock, allowing gravity to sort the ingredients by density. Heavy metals sank to the center. Light silicates rose to the top. Intermediate minerals settled in between. This process, differentiation, is the defining act of planetary formation, the step that transforms a random mixture of material into a structured, layered body. Earth did it. Mars did it. The Moon did it. Mercury, despite being small and close to the Sun, did it. And whatever world had produced the HED meteorites had done it too. The 3 subtypes of head meteorites corresponded to different depths within this layered body. Eucrits, made of basalt, came from the surface, cooled lava flows that once spread across the parent body like the mare basalts on the Moon. Diogenites, coarser and richer in the mineral pyroxene, came from deeper down, the upper mantle, the layer of rock between the basaltic crust and the metallic core. And Howardites were mixtures of both, impact breccias, jumbled combinations of surface and interior material created when impacts excavated deep into the body and mixed material from multiple depths together. Each subtype was a window into a different layer of a differentiated world. Together, they painted a portrait of a body with a fully developed planetary interior, core, mantle, and crust, preserved in meteorites scattered across Earth's surface. But which world? For decades, the parent body of the HED meteorites remained an open question. The chemistry ruled out the Moon and Mars. The isotopic signatures did not match. It ruled out Earth, obviously. The parent body was somewhere out there in the solar system, unknown and unidentified. a differentiated world whose fragments were raining down on Earth, like messages in bottles from a distant shore. The breakthrough came in the early 1970s. Thomas McCord, a young astronomer at the Massachusetts Institute of Technology, had been developing new spectroscopic techniques to study the surfaces of asteroids. Spectroscopy works by breaking light into its component wavelengths, its spectrum. Every mineral absorbs and reflects specific wavelengths in a characteristic pattern, as distinctive as a fingerprint. By measuring the spectrum of sunlight reflected from an asteroid's surface, McCord could determine the mineral composition of that surface without ever visiting it. When McCord and his colleagues turned their spectrometer toward Vesta, the result was immediate and unmistakable. Vesta's surface spectrum was a near-perfect match for the spectrum of eucrite meteorites. The absorption bands aligned. The mineral signatures overlapped. The connection was not suggestive or approximate. It was definitive. McCord had linked a specific family of meteorites found on Earth's surface to a specific world orbiting in the asteroid belt, more than 100 million miles away at its closest approach. It was one of the most elegant acts of cosmic detective work ever performed. The implications were staggering. If the H-Heed meteorites came from Vesta, then Vesta was not merely an asteroid. It was a differentiated body, a world with a metallic core, a rocky mantle, and a basaltic crust. It had experienced volcanic eruptions. Lava had flowed across its surface and cooled into the same kind of basalt found on Earth and the Moon. This 326-mile-wide object had undergone the same fundamental geological process as the terrestrial planets, and we already possessed physical samples of it in our laboratories, delivered free of charge by the violence of interplanetary collisions. To grasp the scale of what Vesta achieved, consider this comparison. Earth's diameter is nearly 7,900 miles. Mars stretches roughly 4,200 miles across. Even our moon spans about 2,160 miles. Vesta, at 326 miles, is smaller than many impact craters on those larger worlds. The Hellas Basin on Mars, a single impact scar, is more than 1,400 miles across. Vesta could fit comfortably inside Hellas with room to spare. The South Pole Aitken Basin on the Moon is roughly 1,500 miles across, nearly 5 times Vesta's diameter. This tiny world accomplished in its first few million years what those vastly larger bodies also accomplished: the complete internal reorganization of a molten sphere into a structured, layered planet. If you shrink the solar system down so that the sun becomes a basketball, Vesta would be an invisible particle of dust, too small to see without a microscope, drifting in the space between the sun and a marble-sized Jupiter. Invisible, seemingly insignificant, yet carrying inside its microscopic frame the full blueprint of how planets are constructed. But the meteorite connection raised one more question, a question that would haunt planetary scientists for the rest of the 20th century and into the 21st. To blast chunks of rock off a body the size of Vesta, chunks large enough and fast enough to escape its gravity, survive millions of years drifting through interplanetary space, and reach Earth's orbit, something cataclysmic must have happened. These were not pebbles gently lifted from the surface by a passing breeze. They were fragments torn from deep within the crust and upper mantle, accelerated past Vesta's escape velocity of roughly 800 miles per hour, and launched on trajectories that would carry them across the inner solar system. What kind of impact could rip pieces from a 300-mile-wide differentiated world without destroying it entirely? And what did the wound look like? Those questions would linger unanswered until instruments grew powerful enough, and eventually until a spacecraft traveled close enough to see the truth written on Vesta's battered face. When that moment finally came, what they found was worse than anyone had imagined. But before we get there, one crucial piece of the foundation remains. How did Vesta melt? This question is more profound than it might seem. Melting a rock requires enormous amounts of heat. On Earth, the interior remains hot, partly because of the planet's sheer size. The mass of the overlying rock creates crushing pressure that generates heat, and partly because of the slow decay of long-lived radioactive elements like uranium, thorium, and potassium. But Vesta is tiny. It does not have the mass to generate significant gravitational heating. and long-lived radioactive elements, while present, produce heat far too slowly to melt a body this small. Vesta should have remained cold, a frozen, undifferentiated lump of primordial rock and metal, indistinguishable from millions of similar bodies in the belt. The answer lies in a short-lived radioactive isotope called aluminum-26. This unstable form of aluminum was abundant in the early solar system, produced by one or more nearby supernovae. Massive stars that exploded and scattered their nuclear ash into the cloud of gas and dust, from which our Sun and its planets were forming. Aluminum-26 has a half-life of only about 717,000 years. This means it decays quickly, releasing heat as it does so. In the first few million years of the solar system, before aluminum-26 had decayed away, any body that had formed and accumulated enough of it would have been heated from within, and the heat was intense. Calculations show that a body the size of Vesta, if it formed within the first 1 to 2 million years after the solar system's birth, would have incorporated enough aluminum-26 to raise its internal temperature above the melting point of rock, roughly 1,200 degrees Celsius. The entire interior would have liquefied, allowing the heavy iron to sink to the center and the lighter silicates to rise to the surface. Differentiation would have occurred rapidly, within perhaps 1 million years, producing the layered structure that we observe today. The timing is critical. If Vesta had formed even 5 million years later, most of the aluminum-26 would have already decayed. There would not have been enough heat to melt the interior. Vesta would have remained a cold, primitive, undifferentiated body, geologically dead from the moment of its formation. The fact that Vesta is differentiated tells us, with remarkable precision, when it formed, very, very early, within the first 1 to 3 million years of the solar system's existence. It is, in the most literal sense, one of the oldest intact worlds we have ever studied, older in its current form than Earth, older than Mars, older than the Moon. Those larger bodies continued to grow and change for tens of millions of years after Vesta had already solidified. Vesta is a snapshot of the solar system's infancy, frozen in stone and iron before the planets had even finished forming. For most of the 20th century, Vesta existed as an abstraction. Scientists had built a compelling circumstantial case. Vesta was differentiated, its surface was basaltic, its meteorites told a story of internal melting and geological complexity that rivaled any world in the inner solar system. But the details remained hidden behind hundreds of millions of miles of empty space. What did Vesta actually look like? What was the shape of this world that had produced those mysterious volcanic rocks? What events had scarred its surface deeply enough to send fragments hurtling across the inner solar system and into the hands of researchers on Earth? The frustration was palpable. Throughout the 1970s and 80s, astronomers had attempted to observe Vesta using ground-based telescopes, employing every technique available: speckle interferometry, adaptive optics in its early and imperfect forms, occultation timing, as Vesta passed in front of distant stars. Each method provided tantalizing scraps of information. Speckle interferometry hinted at an irregular shape. Occultation events provided crude diameter estimates. Light curve measurements, tracking how Vesta's brightness changed as it rotated, revealed a rotation period of roughly 5.3 hours and suggested that one hemisphere was darker or differently textured than the other, but none of these methods could produce an actual image of the surface. Vesta remained, visually, a point of light, a dot that astronomers could measure and analyze but never truly see. Part of the difficulty was sheer distance. At its closest approach to Earth, Vesta lies roughly 100 million miles away. Even at that range, roughly the distance from the Sun to the Earth, its angular size is tiny, roughly half an arcsecond in diameter. For comparison, the full Moon spans about 1,800 arcseconds across. Vesta, from Earth, appears roughly 3,600 times smaller than the Moon. Resolving surface features on an object this small requires either extraordinary optical precision or extraordinary proximity. Ground-based telescopes, even large ones, are fundamentally limited by atmospheric turbulence, the shimmering and distortion caused by temperature variations in Earth's atmosphere. This turbulence blurs images at scales of roughly 1 arcsecond under typical conditions, far too coarse to resolve Vesta's disk. The first real glimpse came in 1996. The Hubble Space Telescope, orbiting Earth at an altitude of roughly 340 miles, turned its primary mirror toward the asteroid belt. Hubble was never designed for asteroid science. Its mission was to peer into the deep universe, galaxies billions of light-years away, nebulae where stars are born and die, the faint afterglow of the Big Bang itself. But its extraordinary optical precision, unblurred by the shimmering effects of Earth's atmosphere, made it the sharpest eye humanity had ever pointed at the sky. When Hubble focused on Vesta, the images it returned were modest by the standards of planetary exploration. The asteroid appeared as a small, pixelated disk, only a handful of pixels across, like a blurry photograph taken from too great a distance. But those few pixels were enough to change everything. There was a hole in Vesta's southern hemisphere, a vast circular depression that appeared to engulf nearly the entire bottom half of the asteroid. It was not subtle. Even in Hubble's fuzzy images, the depression was unmistakable, a gaping absence of material that distorted Vesta's overall shape, making the southern hemisphere visibly flatter than the northern. At the center of this depression, a towering peak rose from the basin floor, a central mountain whose height appeared extraordinary for a body this small. The scale was beyond intuition. It was as if someone had driven an enormous spoon into a ball of clay and scooped out nearly half of it, leaving a single jagged spike of material standing in the center of the cavity. The Hubble observations of Vesta were led by a team including Ben Zellner and Alex Storrs, who published their analysis in a paper that transformed the scientific community's understanding of this asteroid. Prior to the Hubble images, many scientists had assumed that Vesta, despite its spectroscopic evidence of differentiation, would resemble other observed asteroids, roughly potato-shaped, cratered, geologically unremarkable from a topographic standpoint. The revelation of the enormous southern basin shattered those assumptions. This was not a normal asteroid. This was a body that had survived an impact so energetic that it should, by all conventional expectations, have been destroyed. The basin immediately raised questions that would take decades and a dedicated spacecraft mission to answer. What was the composition of the basin floor? How deep did the excavation penetrate? What was the central peak made of? Surface basalt or deeper mantle material dredged up from below? And above all, how had Vesta survived? Scientists studied the Hubble images with growing astonishment and growing concern. Preliminary measurements suggested that the basin was roughly 310 miles in diameter. Vesta itself, remember, is only 326 miles across. The impact crater covered nearly the full width of the world that contained it. If a proportionally equivalent crater existed on Earth, it would stretch from the North Pole to somewhere south of the equator, a wound encompassing half the planet's surface. There would be no recognizable Earth left. The central peak at the basin's center, later confirmed by spacecraft measurements to reach approximately 14 miles above the surrounding terrain, rivaled the height of Olympus Mons on Mars when measured from base to summit, and it existed on a body less than 1/20th of Mars's diameter. This mountain, standing on a world you could drive across in an afternoon, was among the tallest mountains in the entire solar system. The formation of central peaks in impact craters is itself a remarkable phenomenon. When a large impactor strikes a planetary surface, the initial contact creates a transient cavity, a temporary hole blasted into the ground by the sheer force of the collision. In the fractions of a second that follow, the floor of this cavity rebounds upward, driven by the elastic response of the compressed rock beneath. It is the same principle that causes a water droplet to bounce upward when something is dropped into a pool. The surface deforms downward, then rebounds. In an impact crater, this rebound can push material miles above the original surface level, creating a central peak, or, in the largest craters, a ring of peaks. On Vesta, the rebound was so extreme, driven by the extraordinary energy of the Rhea Silvia impact and the relatively weak gravity that could not suppress it, that the central peak rose to rival the greatest mountains in the solar system. The mountain itself is a testament to the violence of the event that created it. Scientists name this basin Rhea Silvia after the mythological Vestal Virgin who, according to Roman legend, was the mother of Romulus and Remus, the twin founders of Rome. The name was fitting in ways that went beyond mythology. Just as the legendary Rhea Silvia gave birth to the founders of a civilization, the Rhea Silvia impact had given birth to an entire family of asteroids, and ultimately to the meteorites that had first drawn scientists' attention to Vesta's remarkable nature. The impactor that created Rhea Silvia was likely between 30 and 50 miles in diameter. To put that in perspective, the asteroid believed to have caused the mass extinction that killed the dinosaurs 66 million years ago, the Chicxulub impactor, was roughly 6 to 9 miles across. The body that struck Vesta's south pole was at minimum 3 times larger than the rock that ended the age of reptiles on Earth, and possibly 7 or 8 times larger. It arrived at a velocity of several miles per second, a typical collision speed in the asteroid belt, where objects orbit the Sun at different speeds and on different tilted paths, making their encounters violent and unpredictable. The energy released in that moment of contact defies human comprehension. Impact physicists have estimated it at roughly 1 million trillion joules. That number means nothing to the human mind. It is simply too large to grasp intuitively. So consider it this way. The largest nuclear weapon ever detonated by human beings was the Soviet Tsar bomber, tested in October of 1961 over the Arctic archipelago of Novaya Zemlya. It released energy equivalent to roughly 50 megatons of TNT. The Rhea Silvia impact released energy equivalent to roughly 1 trillion Tsar bombers. 1 trillion. If you detonated every nuclear warhead ever built by every nation on Earth, all at once, and then repeated that apocalypse a million times over, you would still fall short of the energy that was delivered to Vesta's south pole in a single instant, roughly 1 billion years ago. The impact excavated billions of cubic miles of rock from Vesta's surface and interior. It punched clean through the basaltic crust, which is estimated to be roughly 10 to 30 miles thick, and drove deep into the underlying mantle, possibly reaching within a few dozen miles of the iron core itself. Material was blasted outward at velocities far exceeding Vesta's escape speed of roughly 800 miles per hour. That debris entered independent orbits around the Sun, forming the sober-called Vestoid family, a swarm of smaller asteroids, numbering in the thousands, that still trace similar orbital paths through the asteroid belt today. These Vestoids are literal pieces of Vesta. They carry the same spectral signature, the same mineral composition, the same story of differentiation and catastrophe. Some have remained in the main belt, slowly spreading along their shared orbital path. Others, nudged over millions of years by gravitational resonances with Jupiter, have migrated into the inner solar system. Their orbits now cross the paths of Mars and Earth, and some of those Earth-crossing fragments have, over the ages, intercepted our planet, burned through the atmosphere as fireballs, and landed on the surface as the Hede meteorites that Thomas McCord identified in the 1970s. The chain of causation, when laid out in full, is one of the most remarkable in all of planetary science. A massive body strikes Vesta roughly 1 billion years ago. The collision carves a crater nearly as wide as Vesta itself. Billions of tons of debris are ejected into independent solar orbits. Over hundreds of millions of years, gravitational perturbations nudge some of that debris inward, past Mars, toward Earth. The fragments enter our atmosphere at tens of thousands of miles per hour, their outer layers burning away in streaks of light. The surviving cores slam into deserts, ice sheets, and open fields. Millennia later, a human being picks up a strange rock, carries it to a laboratory, slices it open with a diamond saw, and reads the chemical signature of a catastrophic event that happened a billion years ago on a world more than 100 million miles away. We hold the ancient violence of the solar system in our hands, and for most of human history, we had no idea what we were holding. But here is the problem. Rhea Silvia is not the only giant impact basin on Vesta. Beneath it, partially overprinted and clearly older, lies another enormous depression called Venenea. Named after one of the original Vestal Virgins of Roman history, Venenea is roughly 250 miles in diameter, smaller than Rhea Silvia, but still staggeringly large relative to Vesta's total size. The Venonea Basin is partially concealed beneath the younger Rhea Silvia Basin, like a deeper wound buried beneath a fresher scar. But its outline remains detectable in the topographic data, its rim still traceable as a subtle arc in the terrain. Its existence reveals that Vesta suffered not one but at least two world-reshaping impacts over its lifetime. Let that sink in. A world only 326 miles across was struck by two separate impactors, each one large enough to carve a basin spanning the majority of its diameter. Each of those impacts released enough energy to exceed the gravitational binding energy of a typical undifferentiated asteroid of similar size, meaning that, by rights, each one should have been lethal. Each impact would have been, if directed at Earth, an event so catastrophic that no complex life would have survived. And Vesta absorbed both of them. It was reshaped. It was scarred. It lost a significant fraction of its total mass. Estimates suggest the Rhea Silvia impact alone may have ejected roughly 1% of Vesta's mass into space. But it held together. It survived. The sequence of the two impacts matters. Venonea came first. Its age, estimated from the crater density on the portions of its floor that survive beneath Rhea Silvia, places it roughly 2 billion years ago. A time when Vesta had already been orbiting quietly for more than 2.5 billion years, slowly accumulating small craters, its surface aging in the steady rain of micrometeorites and occasional larger impacts that characterizes the modern asteroid belt. Then, without warning, a body tens of miles across struck the southern hemisphere and excavated a basin that covered most of the visible hemisphere. The energy was enough to shake the entire asteroid, to fracture the crust along the equator, to eject enormous volumes of rock into space. But Vesta's core held. Its layered structure absorbed the blow and redistributed the energy, preventing the kind of runaway fragmentation that would have destroyed a less structurally coherent body. Then, roughly 1 billion years later, perhaps a billion years ago, perhaps slightly more, a second impactor struck in nearly the same location. This was not coincidence. The southern hemisphere already bore the depression left by Venonea, and the altered topography may have made this region geometrically more likely to be struck again. A lower standing surface presenting a larger cross-section to incoming debris from certain orbital directions. The second impact, Rhea Silvia, was even more violent than the first. It drove deeper, excavated more material, raised a higher central peak, and it partially obliterated the evidence of its predecessor, overprinting Venonea's southern regions with its own younger topography. The geological record at Vesta's south pole is a palimpsest of destruction. Two chapters of catastrophe written on top of each other, the older text visible only where the newer text failed to reach. This survival is itself one of the most challenging puzzles in impact physics. Computational simulations of the Rhea Silvia event consistently show that the energy delivered to Vesta was close to, and by some estimates exceeded, the critical threshold for catastrophic disruption. That is the technical term for what happens when an impact delivers enough energy to fragment a body and scatter at least half of its mass to escape velocity, ensuring that gravity can never reassemble it. In simpler terms, the models say Vesta should have been shattered into a cloud of expanding rubble, a new family of small asteroids with no surviving parent body, and yet it was not destroyed. Why? The answer, scientists believe, lies precisely in the feature that makes Vesta scientifically remarkable: its differentiated structure. An undifferentiated asteroid of Vesta's size, a so-called rubble pile held together by weak self-gravity, with no internal structure beyond randomly packed rocks and dust, would almost certainly have been destroyed by the Rhea Silvia impact. Rubble pile asteroids have essentially no tensile strength. They are held together by gravity alone, and a sufficiently powerful impact can easily overwhelm that gravity, blowing the body apart permanently. Many of the asteroid families observed in the belt today are believed to have formed exactly this way. The parent body was destroyed, and the fragments now orbit independently, a cloud of debris where a single body once existed. But Vesta is not a rubble pile. It is a solid, layered, structurally coherent body with a dense iron core at its center, a core estimated to be between 136 and 144 miles in diameter, accounting for roughly a quarter of Vesta's total width and a substantial fraction of its total mass. That core is a concentration of dense material that resists disruption. It acts as a gravitational anchor, binding the overlying mantle and crust even when enormous amounts of material are stripped away from the surface. The mantle and crust themselves are solid rock, not loose gravel but continuous, mechanically strong material that transmits and dissipates shockwaves far more effectively than a loose aggregate would. In a very real sense, the same process that made Vesta extraordinary, its early and thorough differentiation, is also what saved it from destruction. Had Vesta remained a cold, primitive, undifferentiated body, the Rhea Silvia impact would have been its death. Its planet-like architecture was not merely a scientific curiosity, it was a survival mechanism, proven against the most extreme violence the asteroid belt could deliver, and it gets worse. The Rhea Silvia impact did not merely excavate a crater, it sent shockwaves radiating through Vesta's entire body. Powerful compression waves that travelled through the solid interior at speeds of miles per second, bouncing off boundaries between layers, reflecting off the dense iron core and converging on the opposite side of the asteroid from the impact site. This point, the antipodal point, received the focused energy of those converging waves like a target at the center of a magnifying glass. The result was catastrophic deformation of Vesta's equatorial region. Where the shockwaves converged, they cracked the crust open. Enormous troughs, long, deep linear gashes in the surface, appeared, encircling the asteroid like a belt of wounds. The largest of these, Devalia Fossa, stretches more than 240 miles in length, spans up to 14 miles in width, and plunges several miles deep into the crust. If you could stand at the bottom of Devalia Fossa and look upward, the walls on either side would rise above you like the flanks of an impossibly deep canyon, miles of sheer ancient rock fractured and exposed by the propagation of a shockwave from the opposite side of the world. These troughs are not surface scratches. They are structural failures, fractures that penetrate deep into Vesta's crust, evidence that the Rhea Silvia impact stressed the entire body to its mechanical limits. A second, older set of troughs exists as well, partially obscured by the Rhea Silvia era features. These older grooves circle Vesta at a different angle and orientation, and they are associated with the Venenea impact, evidence of a previous era of global stress and fracturing, written onto the surface long before Rhea Silvia overwrote parts of the record. Vesta's surface is a palimpsest, a document rewritten multiple times, each layer of text recording a different chapter of violence. The troughs reveal something crucial about Vesta's mechanical properties. For fractures to propagate across the entire body in this coherent, organized fashion, Vesta must be structurally continuous, a solid object through which mechanical waves can travel, not a loose assemblage of fragments and gravel barely held together by gravity. Seismic waves require a medium to travel through. They cannot cross voids or loose boundaries. The existence of antipodal troughs is direct evidence that Vesta is mechanically intact. A genuine solid body with planet-like structural properties, not an overgrown pile of rubble. The implications of this are underappreciated. Most asteroids, including many that are larger than a few miles across, are believed to be rubble piles, gravitationally bound aggregations of fragments with little or no structural cohesion. They are, essentially, flying gravel heaps. These bodies respond to impacts very differently from solid objects. A shock wave hitting a rubble pile dissipates quickly, absorbed by the countless interfaces between loosely packed fragments. The energy is converted to heat and local rearrangement rather than transmitted coherently across the body. A rubble pile cannot support the kind of organized, globe-spanning fractures that Devalia Fossa and its companion troughs represent. Vesta's troughs are therefore something like a seismological experiment performed by nature. An impact event so energetic that it effectively rang Vesta like a bell, and the fracture patterns it produced on the far side serve as a record of how the interior transmitted that ringing. Scientists have used computational models to simulate the propagation of shock waves through various hypothetical internal structures for Vesta, adjusting the sizes and densities of the core, mantle, and crust until the model predictions match the observed fracture patterns. The results consistently indicate a large, dense core and a mechanically competent mantle, exactly the structure predicted by the head meteorite analysis decades earlier. The troughs and the meteorites tell the same story, arrived at by completely independent lines of evidence. There is an almost poetic symmetry to this. The violence that nearly destroyed Vesta also provided the clearest evidence of the internal structure that saved it. Without the Rhea Silvia impact, scientists would have no troughs to study, no fracture patterns to model, no seismological data to interpret. The catastrophe that came closest to killing Vesta was also the event that most clearly revealed its nature. Destruction and revelation intertwined in a single moment of contact. Beyond the two giant basins and their associated troughs, Vesta's surface tells a longer, slower, more persistent story of violence. The entire surface is saturated with craters of all sizes, from tiny pits a few yards across to degraded basins tens of miles in diameter. Each crater is a record of an individual impact event, a moment when a smaller body, traveling at miles per second, struck Vesta's surface and excavated a hole in the ancient rock. The density of craters varies across the surface, and scientists have used that variation to estimate the ages of different terrain. Heavily cratered regions are old. They have been accumulating impacts for billions of years. Lightly cratered regions, such as the floor of the Rhea Silvia basin, are relatively young. Their surfaces were wiped clean by the basin-forming impact and have had less time to accumulate new scars. The technique is called crater counting, and it is one of the fundamental tools of planetary science. It works on a simple principle. An older surface has been exposed to the rain of impactors for a longer time, and therefore accumulates more craters. By counting the number of craters per unit area, and comparing that number to the known or estimated rate of impacts in the asteroid belt over time, scientists can calculate when a given surface was last reset, that is, when it was last resurfaced by a large impact, a volcanic flow, or some other geological process that erased existing craters and started the clock from zero. On Vesta, crater counting has produced a geological timeline of remarkable precision. The most heavily cratered terrains in the northern hemisphere appear to date back to the earliest history of the solar system. Surfaces that have been accumulating impacts for close to 4 billion years, perhaps longer. The Venenea Basin floor, partially overprinted by Rhea Silvia but still identifiable in areas beyond the Younger Basin's rim, shows a crater density consistent with an age of roughly 2 billion years, placing the Venenea impact solidly in the Middle Proterozoic era on Earth, a time when our planet was covered by single-celled organisms and the atmosphere contained almost no free oxygen. The Rhea Silvia Basin floor, the youngest large surface on Vesta, has a crater density suggesting an age of roughly 1 billion years, roughly contemporaneous with the emergence of multicellular life on Earth, though the connection is, of course, purely coincidental. These age estimates are imperfect. The impact flux in the asteroid belt is not constant over time. It was much higher during the solar system's early history, during the period called the Late Heavy Bombardment, and has declined since. Models of how the impact rate has changed over 4.5 billion years introduce significant uncertainty into crater counting age estimates, but the relative ordering is robust. The northern highlands are the oldest terrain. Venenea is younger, Rhea Silvia is younger still, and the smallest, freshest craters scattered across all terrains represent the most recent impacts. Events that may have occurred as recently as a few million years ago, delivering fresh scars to a surface that has been accumulating wounds since before life existed on Earth. Among the most intriguing features are so-called dark material deposits, patches of unusually dark terrain scattered across Vesta's otherwise bright basaltic surface. These dark splotches puzzled scientists when they were first observed in high-resolution images. Vesta's native rock is highly reflective, the same bright basalt that gives Vesta its distinctive high albedo. So where did the dark material come from? Chemical analysis provided the answer. The dark deposits are rich in carbon and hydrogen-bearing minerals, materials that do not form on Vesta, but are common in a class of primitive, dark asteroids called carbonaceous chondrites. These are ancient, unmelted bodies from the outer regions of the asteroid belt, rich in organic compounds and water-bearing minerals. Over billions of years, some of these dark asteroids collided with Vesta at relatively low speeds, depositing their carbon-rich material on the bright basaltic surface like dark paint splattered on a white wall. The contrast between Vesta's bright native basalt and the dark delivered material creates a striking visual patchwork, a map of collisional history visible from orbit. This mixing of foreign material into Vesta's surface reveals something important about the dynamics of the asteroid belt over deep time. The belt is not a static collection of objects frozen in their original positions. It is a dynamic environment where material is constantly being exchanged between bodies. Objects from the outer belt, rich in carbon and water, drift inward and collide with objects in the inner belt. Objects from the inner belt are nudged outward or scattered by resonances. Over 4.5 billion years, this slow stirring has mixed materials from across the belt, and possibly from beyond it, depositing traces of diverse origins on the surfaces of survivors like Vesta. Vesta's surface is not just a record of its own history. It is a composite record, a museum of the belt's ongoing evolution, with exhibits delivered by countless visitors from across the solar system. There is another layer of mystery in the dark material deposits. Some of them appear to be concentrated in and around certain craters, suggesting that they were delivered by specific, identifiable impact events. In other cases, the dark material appears as diffuse halos or streaks, suggesting that it was distributed by smaller, more numerous impacts or by the gardening effects of micrometeorite bombardment over long timescales. The distribution patterns are complex and not yet fully understood, and they remain an active area of research. Every dark spot on Vesta's surface is a puzzle, a question about when a particular impactor arrived, where it came from, and how much of its material was retained versus how much was scattered back into space by subsequent impacts. Now consider the deeper question that all of this raises, a question that moves beyond Vesta itself and touches the fundamental nature of our solar system. Vesta formed in the first few million years after the Sun ignited. Its interior melted and differentiated within perhaps 1 to 3 million years of its formation, powered by the decay of the short-lived radioactive isotope aluminum-26. This isotope, with a half-life of only about 717,000 years, was injected into the solar nebula by a nearby supernova explosion, or by the radiation of massive young stars in the Sun's birth cluster. Any body that formed early enough incorporated aluminum-26 before it decayed away. And as it decayed, it released heat, tremendous amounts of heat, enough to melt a body the size of Vesta from the inside out. This tells us something profound about timing. Vesta formed so early that it caught the tail end of a radioactive heat pulse that would soon fade away. Bodies that formed even a few million years later, most of the asteroids we see in the belt today, missed that window. They remained cold, undifferentiated, primitive. Vesta's early formation is what gave it the heat to differentiate, the structure to survive, and the geological complexity that makes it unique. If Vesta had formed 5 million years later, it would be just another dark, cold, featureless boulder in the belt. Timing was everything, and the violence did not end with the two giant impacts. Between and after those catastrophic events, Vesta endured a continuous, lower-level bombardment that has never truly stopped. During the period known as the Late Heavy Bombardment, a cataclysmic era, roughly 3.8 to 4.1 billion years ago, when a gravitational rearrangement of the outer planets destabilized vast populations of small bodies and sent them cascading through the inner solar system. The impact rate across the entire inner solar system increased dramatically. On the Moon, this period is recorded as the scarred and saturated surface of the lunar highlands, where craters are packed so densely that every new impact obliterates an older one. On Earth, the evidence has been largely erased by geological recycling, but a handful of ancient impact structures and a spike in impact-related materials in the geological record hint at the intensity of the bombardment. On Vesta, the late heavy bombardment left its mark in the heavily cratered terrain of the northern hemisphere. These are some of the oldest surfaces on Vesta, terrain that has been accumulating impacts since the solar system's earliest era, their crater densities consistent with 4 billion or more years of exposure. Some of these craters are so degraded, their rims worn down, their floors filled with debris from later impacts, their walls slumped and softened by the relentless gardening of micrometeorite bombardment, that they are barely recognizable as craters at all. They appear as shallow, circular depressions, ghostly outlines in the topography, their once sharp features blurred by eons of subsequent violence. They are the faded scars of an era when the solar system was far more dangerous than it is today, an era that Vesta survived, as it has survived everything else. And here is what makes all of this connect to something larger. Vesta is not just a curiosity, it is a witness. It formed before Earth existed, before Mars existed, before the Moon existed. It watched, if a blind, silent rock can be said to watch, as the inner solar system assembled itself through eons of violence. It survived the era of giant impacts that built the terrestrial planets. It survived the late heavy bombardment, the period roughly 3.8 to 4.1 billion years ago, when a gravitational rearrangement of the outer planets sent a rain of comets and asteroids cascading through the inner solar system, cratering every surface, boiling oceans, sterilizing worlds. It survived the ongoing, lower-level bombardment of the past 3.5 billion years. Something is wrong with our assumptions when we look at the asteroid belt and see a graveyard. Vesta is not dead. It is a monument, a standing record of everything that has happened in this region of space since the sun first ignited. And the fact that it survives at all, that it was not shattered or ground to dust or ejected from the solar system, is itself a piece of evidence, a clue about the conditions, the physics, and the sheer improbability of the universe we inhabit. Every day that Vesta continues to orbit is another day of accumulated testimony. Its surface is a palimpsest of violence, a record written in impact craters and fractured troughs and dark foreign deposits, each layer chronicling a different epoch of solar system history. No other body in the inner solar system carries this complete a record. Earth has recycled its surface through plate tectonics. Venus has resurfaced itself with volcanic floods. Mars has eroded and buried its oldest features beneath billions of years of dust. Only Vesta retains its original architecture, scarred but readable, ancient but intact. But here is what makes this truly terrifying. Understanding what Vesta is and what happened to it was not the hard part. The hard part was getting there. Building a spacecraft capable of traveling 1.8 billion miles through interplanetary space, entering orbit around a tiny and irregularly shaped body with weak and uneven gravity, studying it for over a year, and then leaving to visit another world entirely. That mission, the Dawn mission, is a story of engineering audacity, political perseverance, and scientific discovery pushed to the very limit of what human technology can achieve. The story of how humanity reached Vesta begins not with a rocket or a telescope, but with a frustrated physicist and a seemingly impossible idea. In the late 1990s, Christopher Russell, a planetary scientist at the University of California, Los Angeles, sat in his office surrounded by data from every major planetary mission of the previous 3 decades, Voyager, Galileo, Magellan, Mars Global Surveyor, and recognized a glaring gap. We had explored the gas giants. We had mapped Venus beneath its clouds. We had studied Mars's surface in extraordinary detail, but we had never visited the asteroid belt with anything more than a passing glance. The Pioneer and Voyager missions had flown through it on their way to the outer planets, but they had not stopped. They had not lingered. They had not studied a single asteroid up close, and the 2 largest objects in the belt, Ceres and Vesta, the surviving protoplanets, the relics of the solar system's formation, remained virtually unexplored. Russell understood something that many of his colleagues did not yet fully appreciate. Vesta and Ceres were not merely asteroids. They were planetary embryos. They represented a stage of planetary formation that had been erased everywhere else in the inner solar system, erased by the very process of planet building, which had consumed and absorbed all the other embryos into the finished products we call Mercury, Venus, Earth, and Mars. Vesta and Ceres were the only survivors of that era. Studying them was not just asteroid science, it was planetary archaeology, the chance to examine the raw ingredients and intermediate stages of planet formation, preserved in a state that no longer exists anywhere else. The problem was getting there. And not just getting there, staying there. A flyby mission, the kind that had worked so well for the outer planets, would not suffice. A spacecraft screaming past Vesta at miles per second would have only minutes to collect data. A snapshot, not a portrait. What Russell wanted was an orbiter, a spacecraft that could travel to Vesta, slow down, enter orbit, and spend months circling the asteroid at different altitudes, mapping its surface in extraordinary detail, measuring its gravity field, analyzing its mineral composition, and building the kind of comprehensive picture that only sustained observation can provide. And then, this was the audacious part, leave Vesta's orbit, travel to Ceres, and do the same thing there. No spacecraft had ever orbited two different bodies beyond the Earth-Moon system. The energy requirements were staggering. To enter orbit around Vesta, a spacecraft would need to match Vesta's velocity, essentially slow down enough to be captured by Vesta's weak gravity. To leave Vesta and travel to Ceres, it would need to break free of Vesta's gravity and then change course dramatically, targeting a body in a substantially different orbit. Conventional chemical rockets, the kind that had propelled every major planetary mission to date, could not do it. The fuel requirements would be so enormous that the spacecraft would be nothing but a fuel tank with a camera strapped to it, and even then, the math might not close. The answer was a technology that had been tested in space, but never used for a mission of this ambition. Ion propulsion. Unlike chemical rockets, which burn fuel in a brief, explosive burst and then coast, ion engines produce thrust continuously, for months or even years at a time. They work by ionizing a noble gas, typically xenon, stripping electrons from its atoms to create positively charged ions, and then accelerating those ions through an electric field and expelling them at extraordinarily high velocities. The exhaust velocity of an ion engine is roughly 10 times higher than that of the best chemical rocket. This means that for a given amount of propellant, an ion engine can produce far more total change in velocity, the critical currency of space travel. The trade-off is thrust. An ion engine produces a minuscule amount of force at any given moment. The thrust of Dawn's 3 ion engines, operating one at a time, was roughly the weight of a single sheet of paper resting on your palm. If you held a sheet of printer paper flat on your hand and felt its weight pressing down, that whisper of pressure is the force that would carry Dawn across 1.8 billion miles of interplanetary space over 4 years. It is the tortoise of propulsion systems. But the tortoise, as the fable reminds us, wins the race. The reason ion propulsion works despite its laughable thrust is simple: persistence. A chemical rocket fires for minutes. An ion engine fires for months. Over time, that tiny relentless push accumulates into an enormous total velocity change. Dawn's ion engines would eventually log over 54,000 hours of total thrust time, more than 6 years of cumulative operation. No other spacecraft in history has achieved a greater change in velocity under its own power. The gentle push of a sheet of paper, sustained for years, outperformed the explosive fury of traditional rockets. To appreciate the engineering required to make this work, consider the fuel. Dawn carried roughly 937 pounds of xenon, a dense, inert noble gas that was stored as a supercritical fluid in a single large tank at the center of the spacecraft. Xenon was chosen for its high atomic mass, which translates to efficient thrust, and for its chemical inertness, which means it does not corrode the engine components or react unpredictably with other materials on the spacecraft. Over the course of the mission, that xenon would be ionized atom by atom, accelerated through an electric field, and expelled into the vacuum of space at speeds exceeding 90,000 miles per hour, roughly 40 kilometers per second. Each expelled xenon ion carried only a vanishingly small amount of momentum, but there were trillions upon trillions of them, fired continuously for years, and their cumulative effect was an extraordinary total velocity change of roughly 25,000 miles per hour, far more than any conventional chemical mission could achieve with the same. amount of propellant. The power source for the ion engines was equally critical. Unlike spacecraft bound for the outer solar system, which rely on nuclear generators because sunlight becomes too faint beyond Mars, Dawn used solar panels. Two enormous solar arrays, each stretching more than 27 feet in length, unfolded from the spacecraft like wings, presenting a combined area of roughly 380 square feet to the Sun. At Earth's distance from the Sun, these panels could generate over 10,000 watts of electrical power, enough to run a small home. At Vesta's greater distance, where sunlight is roughly one-third as intense as at Earth, power output dropped to roughly 3,000 watts. The entire mission architecture was built around managing this diminishing power budget, ensuring that the ion engines and scientific instruments could operate effectively even as the spacecraft moved farther from the Sun. Russell assembled a team, designed the mission, and submitted a proposal to NASA under the Discovery Program, a line of relatively low-cost planetary missions designed to answer specific scientific questions. The proposal was accepted, then it was nearly cancelled, then it was reinstated, then it was nearly cancelled again. Dawn's journey through NASA's bureaucracy was almost as perilous as its eventual journey through space. The first crisis came in 2003. NASA was facing severe budget pressures, and the agency began looking for missions to cut. Dawn, still in its development phase, was an easy target. It relied on unproven technology. Ion propulsion had only been used once before on a deep space mission by the technology demonstration spacecraft Deep Space One, and that mission had encountered significant technical difficulties. Dawn's spacecraft complex, its trajectory was ambitious, and its timeline was long. Budget reviewers questioned whether the science justified the cost. Christopher Russell fought back. He testified before review boards. He made the case that Vesta and Ceres were not ordinary targets. They were the last surviving witnesses of planetary formation, and the opportunity to study them would not come again. Dawn survived that first challenge. Then came a second. In March of 2006, just 18 months before the planned launch, NASA announced that Dawn was being cancelled outright. The mission, the agency said, was over budget and behind schedule. The team was devastated. Years of work, hundreds of scientists and engineers, a spacecraft that was already partially assembled. All of it was about to be scrapped. Russell refused to accept the decision. He organized a campaign to reverse it, enlisting the support of planetary scientists across the country, writing letters, making phone calls, arguing that cancelling Dawn would be a scientific tragedy. The case was compelling. There was no other mission in development, or even in planning, that could visit both Vesta and Ceres. Ion propulsion was the only technology that made the dual-orbit mission feasible, and Dawn was the only ion propulsion mission aimed at the asteroid belt. If Dawn died, the opportunity might not return for decades. Within days, the planetary science community rallied behind the mission. Letters poured into NASA headquarters from universities and research institutions around the world. The National Academy of Sciences weighed in, noting that the exploration of Vesta and Ceres had been identified as a high priority in the most recent decadal survey. The community's consensus document for prioritizing planetary science missions. Members of Congress expressed concern about cancelling a mission that had already consumed significant resources and was close to completion. The pressure was immense and sustained, and in late March, less than 2 weeks after the cancellation was announced, NASA reversed itself. Dawn was back. The resurrection was virtually unprecedented in the agency's history. Cancelled missions almost never return. The political, bureaucratic, and financial barriers to reviving a dead project are normally insurmountable. But Dawn had something that most cancelled missions lack: a scientific community that was united, vocal, and deeply convinced that the mission's targets were irreplaceable. Christopher Russell's years of advocacy had built a coalition that, at the critical moment, proved strong enough to override the budgetary calculations. It was a triumph of scientific passion over administrative pragmatism, and it would pay dividends beyond anyone's expectations. Dawn launched on September 27, 2007, from Cape Canaveral, Florida, atop a Delta II rocket. It carried three primary instruments: a pair of cameras for imaging Vesta's surface in visible and infrared light, a gamma-ray and neutron detector for measuring the chemical composition of the surface, and a visible and infrared mapping spectrometer for identifying minerals. It also carried the mission's most critical piece of equipment: its three ion engines, each powered by solar arrays that stretched 44 feet from tip to tip, making Dawn one of the largest spacecraft ever sent to the inner solar system. The journey to Vesta took nearly 4 years. Dawn spiraled slowly outward from the Sun, its ion engine burning for months at a time, gradually matching its orbit to Vesta's. Unlike a conventional mission, which follows a ballistic trajectory, a single arc determined by the initial launch and perhaps a few brief course corrections, Dawn's flight path was a continuous spiral, constantly shaped by the gentle thrust of its engines. Mission planners at the Jet Propulsion Laboratory in Pasadena, California, spent years computing this trajectory, accounting for the gravitational influences of every planet, the varying intensity of sunlight as Dawn moved away from the Sun, the gradual depletion of xenon fuel, and the need to arrive at Vesta with precisely the right velocity and approach angle to enter orbit. Along the way, Dawn flew past Mars in February of 2009, using the planet's gravity to bend its trajectory and gain additional speed, a gravitational slingshot that shaved years off the trip. It was a maneuver of extraordinary precision. Dawn passed within 330 miles of Mars's surface, threading a needle at interplanetary velocities, its trajectory calculated down to fractions of a second. During the flyby, Dawn's cameras captured images of Mars that served a dual purpose: calibrating the instruments that would soon be pointed at Vesta and providing a final check that the optics were functioning perfectly after more than a year in space. Mars appeared in those images as a vast russet disk, its craters and volcanoes clearly visible, a familiar world serving as a waypoint on the journey to an unfamiliar one. After the Mars flyby, Dawn continued its spiraling outward cruise for another 2.5 years. The ion engines burned with their quiet, relentless persistence. The spacecraft crossed the orbit of Mars and entered the main asteroid belt. Occasionally, the engines were shut down for brief periods to allow the spacecraft to reorient itself, to communicate with Earth, or to rest components that had been operating continuously for months. But for the vast majority of the transit, Dawn was thrusting, pushing, always pushing, that tiny sheet of paper force, slowly bending the trajectory of a spacecraft half a solar system away from home. On July 15, 2011, Dawn became the first spacecraft to enter orbit around a main belt asteroid. The moment was historic but undramatic. There was no sudden deceleration, no violent braking burn. Dawn simply continued its gentle ion thrust, spiraling closer and closer to Vesta until the asteroid's gravity captured it. The transition from heliocentric orbit to Vesta-centric orbit was seamless, a slow dance of converging trajectories rather than a dramatic capture. Mission controllers at the Jet Propulsion Laboratory monitored the process in near real time, tracking the spacecraft's position through radio signals that took roughly 15 minutes to travel from the asteroid belt to Earth. When confirmation came that Dawn was in orbit, the reaction was quiet jubilation, handshakes, applause, a few tears. 4 years of flight, a decade of development, and a near-death bureaucratic experience had culminated in a spacecraft gently settling into orbit around a world that no human eye had ever seen up close. And then the images started coming in. The approach images, taken during the weeks before orbital capture, as Dawn spiraled inward and Vesta grew from a point of light to a disk to a world, were revelatory in themselves. Scientists watched as features they had glimpsed only as pixelated blurs in Hubble images resolved into vivid, three-dimensional landscapes. The Great Southern Depression grew from a vague darkening into a vast walled basin with clearly defined topography. The central peak emerged as a towering spire of rock, its flanks etched with shadows that revealed slopes and ridgelines. Bright rays of ejecta, material splashed outward from younger impact craters, streaked across the surface like brushstrokes on a dark canvas. The first high-resolution photographs of Vesta's surface exceeded every expectation. This was not the featureless grey boulder that many had predicted. This was a world a battered, complex, geologically rich world with a surface as varied and dramatic as any in the inner solar system. Craters every size, from tiny pits to enormous basins, long, deep troughs encircled the equator. Mountains towered to dizzying heights. Bright and dark patches alternated across the terrain in patterns that hinted at a long and violent geological history. The Ria Silvia Basin, which Hubble had glimpsed as a blurry depression, now stood revealed in staggering detail. The basin was even more dramatic than the Hubble images had suggested. Its walls rose miles above the basin floor, steep escarpments of exposed rock descending toward a roughly circular depression that stretched 310 miles across. At its center stood the central peak, now measured precisely at roughly 14 miles above the basin floor, making it approximately 2.5 times the height of Mount Everest, the tallest mountain on Earth, measured from sea level. On Vesta, this mountain rises from a crater floor that itself sits miles below the surrounding terrain, making the total topographic range from the deepest point in the basin to the summit of the central peak, roughly 22 miles. On a world only 326 miles across, this topographic variation is proportionally extraordinary. If Earth had terrain with the same proportional relief, our deepest canyon would extend down nearly 400 miles, more than halfway through the mantle. Dawn's cameras also revealed the Venenea Basin in unprecedented clarity. The older, partially overprinted basin was now clearly visible in topographic maps, its rim still partially intact beneath the younger Rasilvia features. The two basins overlapped in a way that told a clear story of sequential violence. An older catastrophe followed, perhaps hundreds of millions of years later, by a younger one that partially obliterated the evidence of its predecessor. The numbers are striking. Between the two impacts, Vesta lost an estimated 1% or more of its total mass, roughly 150,000 billion pounds of rock, blasted into space and scattered across the asteroid belt. That debris formed the Vestoid family of asteroids, and some of it eventually reached Earth as meteorites. The Ria Silvia impact alone may have ejected a volume of material equivalent to a sphere roughly 40 miles in diameter, a small world's worth of rock launched into independent orbits around the Sun by a single moment of violence. Dawn spent 14 months orbiting Vesta, circling at different altitudes to study different aspects of the protoplanet's nature. The orbital campaign was divided into distinct phases, each optimized for different scientific goals. In the first phase, called Survey Orbit, Dawn circled at roughly 1,700 miles above the surface. At this altitude, the entire visible disk of Vesta fit comfortably within the camera's field of view, allowing the team to build a comprehensive global map, the first complete photographic atlas of a main belt asteroid. Survey Orbit lasted roughly 3 weeks and produced thousands of images that were stitched together into seamless mosaics, revealing every major feature on the sunlit surface. After Survey Orbit, Dawn spiraled down to its second phase, the high-altitude mapping orbit, at roughly 420 miles above the surface. At this closer distance, surface features that had appeared as vague smudges in the survey images resolved into crisp, detailed landscapes. Individual boulders, tens of yards across, became visible. The texture of crater walls emerged, smooth in some places, rough and fractured in others. The dark material deposits stood out with stark clarity, their boundaries sharp against the surrounding bright basalt. Dawn spent roughly 3 months in this orbit, methodically imaging the surface in overlapping strips that could be combined into topographic maps, measuring the height of every mountain, the depth of every crater, the width of every trough. Then came the most ambitious phase, the low-altitude mapping orbit, at roughly 130 miles above the surface. This close approach brought Dawn within a distance shorter than the drive from New York City to Philadelphia. At this altitude, the spacecraft's instruments achieved their maximum sensitivity and resolution. The gamma-ray and neutron detector could now detect variations in surface chemistry across regions just a few miles wide. The gravity field could be measured with precision, fine enough to distinguish density variations deep within Vesta's interior, and the cameras could resolve features as small as a few dozen yards across. Individual boulders, subtle color variations in the rock, fine fractures that would have been invisible from higher altitude. Operating at this altitude was risky. Vesta's gravity, though weak by planetary standards, is not uniform. The irregular shape of the asteroid and the uneven distribution of mass within its interior create a lumpy gravitational field, stronger in some places, weaker in others. These gravitational anomalies tugged at Dawn's orbit, perturbing its trajectory in ways that required constant monitoring and correction. The flight team at JPL tracked Dawn's position with extraordinary precision using radio signals bounced between the spacecraft and a network of large dish antennas on Earth, the Deep Space Network, to measure Dawn's velocity changes to within fractions of a millimeter per second. Those velocity measurements were then inverted mathematically to produce a map of Vesta's gravitational field, which in turn revealed the internal structure that scientists had long suspected but never directly measured. Vesta's gravity was not uniform. It was stronger in some regions than in others, indicating variations in density beneath the surface. Exactly what one would expect from a differentiated body with a dense iron core, a less dense mantle, and a thin basaltic crust. The gravity field also carried the fingerprint of the Rheasilvia impact. The enormous basin in the southern hemisphere represented a mass deficit, a region where billions of tons of rock had been removed, leaving behind a thinner, lighter section of crust and upper mantle. The gravity in this region was measurably lower than in the intact northern hemisphere, and the difference was precisely quantifiable. But scientists could determine how much mass had been removed and, by extension, how much material had been ejected into space as the Vestoid family of asteroids. The gravity field was, in effect, a weighing scale for the violence that Vesta had endured, a way to calculate the consequences of impacts that occurred a billion years before any human being existed. The gravity data also revealed subtler features. Beneath the surface, density variations hinted at the boundaries between different geological layers. The transition from crust to mantle, from mantle to core, these boundaries were not perfectly smooth or uniform. They showed evidence of disruption and deformation, particularly in the southern hemisphere, where the Rheasilvia impact had pushed and compressed the internal structure. Some scientists interpreted the gravity anomalies as evidence that the impact had partially displaced the core relative to the outer layers, shifting the center of mass of the iron core slightly off-center from the geometric center of the asteroid. If confirmed, this displacement would represent yet another scar of the Rheasilvia event, a permanent dislocation of Vesta's internal anatomy caused by the most violent moment in its history. By combining the gravity measurements with models of Vesta's shape and mass, scientists were able to estimate the size and density of the iron core. The results confirmed what the Heed meteorites had suggested decades earlier. Vesta's core is roughly 136 to 144 miles in diameter, about 40% of Vesta's total width, and its density is consistent with a mixture of iron and nickel, the same metals that form Earth's core. The core contains an estimated 40% of Vesta's total mass, a proportion remarkably similar to Earth's, where the iron core accounts for roughly a third of the planet's mass. In terms of internal structure, Vesta is not merely planet-like. It is, in miniature, almost a twin of the terrestrial planets. Dawn's gamma-ray and neutron detector, known by its acronym GRAND, provided another layer of data, perhaps the most chemically revealing of all. GRAND did not measure reflected light or emitted heat. It measured something far more exotic: the nuclear interactions between cosmic rays and Vesta's surface. Cosmic rays, high-energy particles from deep space, mostly protons traveling at nearly the speed of light, constantly bombard every airless body in the solar system. When these particles strike the surface, they interact with atomic nuclei in the top few inches of soil, generating cascades of secondary particles, gamma rays and neutrons, that carry information about the chemical composition of the target material. Each element produces a characteristic signature, a specific pattern of gamma-ray energies and neutron fluxes that serves as a chemical fingerprint. GRAND was designed to read these fingerprints. It sat on the spacecraft's lower deck, pointed permanently at Vesta's surface, collecting gamma rays and neutrons day after day, orbit after orbit. The instrument was most effective in the low-altitude mapping orbit, where the shorter distance to the surface increased the signal strength. Over weeks of continuous measurement, Grand built a chemical map of Vesta's surface, a map showing the concentrations of iron, titanium, silicon, oxygen, potassium, thorium, and other elements across the entire globe. The results confirmed the basaltic nature of Vesta's surface and revealed something else: the presence of hydrogen. Hydrogen on Vesta's surface was concentrated in specific regions, particularly near the equator and in areas associated with dark material deposits. The source of this hydrogen is almost certainly water, not liquid water, but water molecules or hydroxyl groups bound into the crystal structure of hydrated minerals. And those hydrated minerals were not native to Vesta. They were delivered by impacts from carbonaceous asteroids, dark, water-rich bodies from the outer asteroid belt. This finding was important for two reasons. First, it demonstrated that water-bearing material had been transported from the outer solar system to the inner solar system via asteroid impacts, a process that many scientists believe played a role in delivering water to the early Earth. The chain of reasoning is straightforward but profound. If carbonaceous asteroids could deliver water to Vesta, a small, dry, rocky body in the inner asteroid belt, then they could certainly have delivered water to Earth, which occupies an even more accessible orbit. The water in Earth's oceans may owe its existence, at least in part, to the same class of dark, primitive asteroids that left their calling cards on Vesta's surface. The dark splotches on Vesta are, in this interpretation, evidence not just of collisional history, but of the cosmic plumbing system that made Earth habitable. Second, it showed that even a small, airless, irradiated body like Vesta could retain traces of delivered water over geological timescales. The water was not sitting in pools on the surface, of course. It was locked into mineral structures, shielded from the harsh vacuum of space by the chemistry of the rocks themselves. But it was there, on a body that had no business having any water at all. This finding challenged the assumption that water could not persist on bodies without atmospheres or magnetic fields. Vesta has neither. Its surface is bathed in solar radiation and cosmic rays, exposed to temperature extremes that range from roughly -100 degrees to roughly 0 degrees Fahrenheit, depending on latitude and time of day. And yet the water persisted, bound into minerals, waiting billions of years to be detected by an instrument that did not exist when the water arrived. Dawn's mapping spectrometer, meanwhile, was reading the mineralogical fingerprint of every patch of terrain it passed over. The instrument worked by splitting the reflected sunlight from Vesta's surface into hundreds of individual wavelengths, from the visible range through the near-infrared, and measuring the intensity at each wavelength. Different minerals absorb and reflect light differently, and these differences create distinctive patterns in the reflected spectrum. Pyroxene, the dominant mineral on Vesta's surface, produces a characteristic pair of absorption bands, dips in the reflected light at specific infrared wavelengths that vary in position and depth depending on the exact chemical composition of the pyroxene. By mapping these absorption bands across the entire surface, the spectrometer could determine not just which minerals were present, but which specific varieties, and in what proportions. The results painted a picture of extraordinary geological diversity. The surface was dominated by the mineral pyroxene, specifically a type called low-calcium pyroxene in the northern hemisphere and high-calcium pyroxene in the equatorial and southern regions. This distribution matched the predicted structure of a differentiated body: diogenite-like material, deep mantle rock, rich in low-calcium pyroxene, exposed in areas where impacts had excavated the crust, and eucrite-like material, basaltic surface rock, richer in high-calcium pyroxene, covering the less disturbed regions. The spectrometer was essentially reading Vesta's geology from orbit, confirming that the asteroid's surface was a patchwork of different rock types from different depths. Crust here, upper mantle there, everything mixed and redistributed by billions of years of impacts. The pyroxene map was a triumph of remote sensing, a demonstration that the mineralogical character of a world could be determined from orbit with a precision approaching that of hand sample analysis in a laboratory. Individual craters could be classified by the type of rock they had excavated. Fresh craters that had punched through the basaltic crust to reach the diogenite layer beneath showed distinctive spectral signatures, bright patches of low calcium pyroxene surrounded by the darker, higher calcium basalt of the undisturbed surface. These craters were effectively windows into Vesta's interior, natural drill holes that exposed deeper rock layers for spectroscopic analysis. By mapping the distribution of these windows, scientists could estimate the thickness of the crust in different regions. Thinner in the south, where the Rhea Silvia impact had stripped away miles of overlying rock, and thicker in the north, where the crust had remained relatively intact for billions of years. But perhaps the most surprising discovery was one that scientists had not predicted at all. In several locations, the spectrometer detected olivine, a green mineral that is a major component of planetary mantles, including Earth's. Olivine was expected to be found in Vesta's mantle, deep beneath the surface. The Rhea Silvia impact had penetrated close to the mantle, so some olivine exposure was plausible, but the detected olivine was found in unexpected locations, not concentrated in the Rhea Silvia basin, as models predicted, but scattered in small deposits across the surface. The source and distribution of olivine on Vesta remains a topic of active research and debate. Some scientists argue it was delivered by impacts from external bodies. Others believe it represents deeply excavated mantle material that was redistributed by subsequent impacts. The question is unresolved, and it highlights how much remains unknown about Vesta's geological history even after a comprehensive orbital survey. On September 5, 2012, Dawn fired its ion engines one final time in Vesta's vicinity and slowly spiraled away from the protoplanet, beginning the long journey to its second target, Ceres. The departure was as gradual as the arrival had been, not a dramatic escape burn, but a slow unwinding of the orbital spiral, the ion engine gently adding velocity over weeks until Vesta's gravity could no longer hold the spacecraft. Dawn looked back as it departed, its cameras capturing final images of the receding world, a battered sphere growing smaller against the black of space, its great southern basin shrinking from a landscape into a feature, into a shadow, into nothing, until Vesta was once again what it had been for most of human history, a point of light. The 2.5-year cruise from Vesta to Ceres was, in some ways, as remarkable as the Vesta encounter itself. Dawn's ion engines, having already operated for years, continued their tireless work, slowly reshaping the spacecraft's orbit to intercept the largest body in the asteroid belt. During this transit, the science team was not idle. They spent the journey analyzing the enormous volume of data collected at Vesta. Tens of thousands of images, millions of spectral measurements, a gravity field map of exquisite precision, chemical abundance data from the gamma-ray and neutron detector. The results poured out in a torrent of scientific publications, each one refining the picture of Vesta's nature, each one confirming or complicating the theories that had been built from meteorites and telescopic observations over the preceding decades. Dawn arrived at Ceres in March of 2015, becoming the first spacecraft to orbit a dwarf planet and the first to orbit two extraterrestrial bodies. Its exploration of Ceres, a world utterly different from Vesta, ice-rich and dark, where Vesta was rocky and bright, continued until November of 2018, when the spacecraft finally exhausted its supply of hydrazine fuel, which it used for attitude control. Without the ability to point its antenna at Earth, Dawn fell silent. It remains in orbit around Ceres today, a permanent satellite of the dwarf planet, circling in darkness, carrying its instruments and its memories of two alien worlds. NASA has predicted that Dawn's orbit will remain stable for at least 50 years, and probably for centuries. The spacecraft that traveled nearly 4.5 billion miles across the solar system will spend eternity circling the world it was sent to study, a monument to human curiosity parked in the asteroid belt. But Dawn's departure from Vesta also marked the end of one of the most remarkable engineering achievements in the history of space exploration. The spacecraft had traveled more than 1.7 billion miles from Earth. It had operated its ion engines for a cumulative total of more than 4 years of continuous thrust. It had orbited a body that no spacecraft had ever visited, at altitudes ranging from 1,700 miles to just over 130 miles, and then it left, under its own power, to visit another world. No other spacecraft has ever done this. Dawn remains the only mission in history to have orbited two different extraterrestrial bodies. The math is striking. A spacecraft weighing roughly 2,600 pounds, powered by the force equivalent of a sheet of paper, travelled nearly 2 billion miles, orbited a protoplanet for 14 months, mapped it in exquisite detail, and then departed to do it all over again at a second target. The mission cost roughly $470 million, roughly $1.50 per American citizen, less than the price of a cup of coffee. For that price, humanity gained the first detailed knowledge of a world that has existed since before Earth was born. The engineering legacy of Dawn extends beyond its scientific discoveries. The mission proved that ion propulsion was not merely a theoretical curiosity or a technology demonstration. It was a practical tool for ambitious planetary exploration. Before Dawn, ion engines had been used only on Deep Space One, a small technology test mission that encountered significant problems. Dawn demonstrated that ion propulsion could be relied upon for a mission spanning nearly a decade, involving multiple orbital captures and departures, covering billions of miles, and operating in conditions ranging from the relative warmth near Mars to the deep cold of the outer asteroid belt. Future mission concepts, including proposals to visit multiple moons of Jupiter or Saturn, to rendezvous with distant comets, or to survey families of near-Earth asteroids, now cite Dawn's successes as proof that ion propulsion can enable missions that would be physically impossible with conventional chemical rockets. Christopher Russell, the scientist who conceived Dawn, who fought for it through two near cancellations, who shepherded it from a concept on paper to a spacecraft orbiting an alien world, lived to see his vision vindicated beyond his most optimistic projections. The data Dawn returned from Vesta transformed a point of light into a place, a world with a history, a structure, a personality. It answered questions that had lingered for decades and raised new questions that will drive research for decades more. This is not science fiction. This is what happened. And the story it revealed about Vesta was not just a story about one asteroid. It was a story about the birth of every rocky world in the inner solar system, told by the only surviving witness. There is a moment in every deep investigation, whether in science, in history, or in the slow unraveling of a personal mystery, when the accumulation of facts crosses a threshold and becomes something else, something larger, something that cannot be contained by data alone. The numbers stop being numbers, the measurements stop being measurements, and what remains is a feeling, a quiet, bone-deep recognition that the universe is far stranger, far older, and far more violent than the mind can comfortably hold. This is that moment. Consider what we now know. Vesta is 4.5 billion years old, nearly as old as the Sun itself. It formed from the same cloud of dust and gas that built every planet, every moon, every grain of sand on every beach on Earth. It melted within the first few million years of the solar system's existence, heated by the decay of a radioactive isotope that no longer exists in significant quantities anywhere in the cosmos. Aluminum-26, a ghost element, a remnant of a supernova that exploded before our sun was born. That heat separated Vesta's interior into layers, an iron core, a silicate mantle, a basaltic crust. The same architecture as Earth, the same fundamental process. The only difference is scale. And then Vesta stopped. It cooled, it solidified, its volcanoes went quiet, its interior froze in place, while Earth continued to grow, absorbing more and more material through hundreds of millions of years of relentless bombardment, eventually reaching its current size, developing an atmosphere, forming oceans, giving rise to life. Vesta remained small, frozen, a snapshot of a process that Earth completed, but Vesta never could. Every planet in the inner solar system passed through the Vesta stage. Earth was once a collection of Vesta-like bodies, crashing together and merging and growing. Vesta is what Earth used to be, before Earth existed. Let that sink in. When you look at Vesta, you are looking at Earth's past, not metaphorically, literally. The physical process that built Vesta, accretion, melting, differentiation, is the same process that built Earth. The only difference is that Earth's building blocks were eventually consumed, absorbed into a larger body. their individual identities erased by the very act of planet formation. Vesta is the one that got away. The one building block that was left behind, preserved in its original state, carrying the chemical and thermal fingerprint of an era that no longer exists. What would Earth have looked like at the Vesta stage? This is not an abstract question. It is a question that planetary scientists have tried to answer using Vesta as a model. In the first few million years of the solar system, proto-Earth was not a single body. It was a swarm of embryos, dozens of Vesta-sized and larger bodies, each one molten, each one differentiated, each one carrying its own iron core and basaltic crust. These embryos occupied overlapping orbits in the inner solar system, their paths gradually diverging until gravitational perturbations brought them into collision. The collisions were catastrophic. When two differentiated bodies of similar size collide at miles per second, the edge is sufficient to completely melt both objects, to strip away most or all of their crusts, to partially or fully merge their iron cores, and to scatter debris across the entire inner solar system. The resulting body, larger than either parent, would then cool, re-differentiate, and begin the process of accumulating more material, until the next major collision reshuffled the deck again. This cycle repeated for roughly 50 to 100 million years, an era of serial destruction and reconstruction that gradually built the terrestrial planets from a swarm of small bodies into the four survivors we see today. The last great collision in Earth's history, the moon-forming impact, was simply the final act of a process that had been ongoing since the solar system's birth, and Vesta, sitting in the asteroid belt, watched it all. It was there when the first embryos collided. It was there when proto-Earth doubled in size. It was there when Theia struck the proto-Earth and created the moon. It was there through all of it, a silent witness to the most violent construction project the inner solar system has ever known. This is why scientists care so deeply about Vesta. Not because it is large, it is tiny by planetary standards. Not because it is threatening, it poses no danger to Earth. Not because it is beautiful, though it is, in its own battered and austere way. Scientists care about Vesta because it is a time machine, a physical record of conditions that existed before our planet was born. Studying Vesta is, in a very real sense, studying the infancy of Earth itself, an infancy for which no other evidence survives. The head meteorites that have been falling to Earth for billions of years are samples of this time machine. When a scientist in a laboratory holds a eucrite meteorite in her hands, she is holding a piece of volcanic rock that formed 4.5 billion years ago on a world that no longer has volcanic activity of any kind. The lava that cooled into that rock flowed across Vesta's surface in an age when the solar system was still under construction, when Earth was nothing more than a chaos of colliding fragments, when the sun itself was still settling into its main sequence existence. The age of that rock predates every fossil ever found on Earth. It predates the formation of Earth's oceans. It predates the moon-forming impact, the colossal collision between the proto-Earth and a Mars-sized body called Theia that created our moon roughly 4.5 billion years ago. Vesta's volcanic rocks solidified before that cataclysm occurred. They are older than the moon. The implications cascade outward from this single fact. If Vesta differentiated so quickly, within the first few million years of the solar system, then the conditions for differentiation must have been present extremely early. The radioactive heat source, aluminum-26, must have been uniformly distributed throughout the solar nebula, or at least throughout the inner regions where rocky planetesimals formed. This, in turn, tells us something about the environment in which our sun was born. Aluminum-26 is produced in the interiors of massive stars and ejected into space when those stars explode as supernovae. Its presence in the early solar system means that a massive star exploded near the sun's birth site shortly before, or even during, the sun's formation. Our star was born in a violent neighborhood. The shockwave from a dying star may have actually triggered the collapse of the gas cloud that became our sun. In a sense, a star had to die for our star to be born, and Vesta carries the evidence of that death in the isotopic signatures of its rocks. The precision of these isotopic measurements deserves attention because it is one of the great unsung achievements of modern analytical chemistry. When scientists measure the abundance of aluminum-26 in a head meteorite, They are not detecting the isotope itself. It decayed away billions of years ago, its half-life of 717,000 years, ensuring that essentially none remains today. Instead, they measure its decay product, magnesium-26. When an aluminum-26 atom decays, it transforms into a magnesium-26 atom. By measuring the ratio of magnesium-26 to other magnesium isotopes in minerals that originally incorporated aluminum but no magnesium, a mineral called anorthite, for example, which is common in eucrite meteorites, scientists can work backward to determine how much aluminum-26 was present when the mineral crystallized. This, in turn, constrains the time of crystallization, because the abundance of aluminum-26 was decreasing exponentially as it decayed. The more aluminum-26 present at crystallization, the earlier the crystallization occurred. The calculations are demanding. They require measuring isotopic ratios to precisions of parts per 10,000, detecting tiny excesses of one type of magnesium atom amid billions of other atoms. The instruments that perform these measurements, secondary ion mass spectrometers, or SIMS, focus a beam of charged atoms onto a polished surface of meteorite material, sputtering away a microscopic volume of rock and feeding the liberated atoms into a mass spectrometer that sorts them by weight with extraordinary accuracy. The technique is essentially reading a chemical clock that stopped ticking 4.5 billion years ago and reading it accurately to within a few 100,000 years. On the timescale of the solar system, that is like determining the time of day to within a minute. These measurements have produced one of the most remarkable results in all of cosmochemistry. Eucrite meteorites from Vesta show excess magnesium-26 in their calcium-aluminum-rich minerals, confirming that Vesta formed while aluminum-26 was still live and actively decaying. The magnitude of the excess is consistent with Vesta accreting and melting within 1 to 3 million years after the formation of the solar system's first solids. Objects called calcium-aluminum-rich inclusions, or CAIs, which are found in primitive meteorites, and are generally accepted as the oldest objects in the solar system, dated to 4,567,000,000 years ago, plus or minus a few 100,000 years. Vesta, therefore, formed when the solar system was younger than 3 million years old. To put this in perspective, if the entire history of the solar system were compressed into a single calendar year, Vesta completed its formation and differentiation before midnight on January 1st. There is something almost unbearable about this chain of connections. A star dies. The shockwave triggers the formation of a new star, our Sun. The radioactive debris from the dying star is incorporated into the new solar system's building blocks. That debris heats the building blocks, melting them, differentiating them. One of those building blocks, Vesta, survives intact for 4.5 billion years. Pieces of it are blasted off by impacts and fall to Earth as meteorites. Scientists pick up those fragments and read in their chemistry the fingerprint of a supernova that exploded before our Sun existed. The dead star's signature is preserved in a rock that landed in a desert on a planet that did not exist when the star died. The connections span billions of years and hundreds of light years of space, and they are preserved in fragments small enough to hold in your hand. But the philosophical weight of Vesta extends beyond its role as a time capsule. Vesta also forces us to confront the violence that is fundamental to the existence of worlds like Earth. We tend to think of our planet as a haven, a quiet, blue, temperate world, protected by its atmosphere and magnetic field, blessed with the conditions for life. But Earth was not always this way. Earth was built by violence. It was assembled from the wreckage of countless small worlds like Vesta, worlds that collided and merged, their individual identities obliterated in the fire of impact after impact after impact. The very iron that forms Earth's core, the iron that generates our magnetic field, that shields us from solar radiation, that makes life possible, was delivered by the same kind of catastrophic collisions that scarred Vesta. Earth's iron core is made from the cores of 1,000 Vestas, merged and melted, and combined over millions of years of relentless accretion. This statement is not poetic license. It is a quantitative observation supported by the physics of accretion. Earth's mass is roughly 80 times greater than Vesta's. Its iron core contains roughly 30% of its total mass. That iron had to come from somewhere. It could not have been delivered by primitive, undifferentiated bodies alone. Those contain iron mixed uniformly with silicates, distributed throughout the rock in small grains, not concentrated into a dense metallic core. The efficient separation of iron from silicate, the process that created Earth's distinct core and mantle, was facilitated by the prior differentiation of the building blocks. The embryonic worlds that collided to form Earth had already sorted themselves internally. Their iron had already sunk to form small cores. When those embryos collided, their pre-sorted iron cores merged more readily, accelerating the growth of Earth's own core. The differentiation of Earth was not a single event. It was the culmination of 1 billion smaller differentiations, each one occurring inside a Vesta-like body in the first few million years of the solar system. Every atom of iron in your blood was once inside a differentiated body like Vesta. It was part of a core. It was surrounded by a mantle of silicate rock. It was protected by a crust of solidified lava. And then that body was destroyed, smashed into another body, its core ripped open, its contents mingled with the contents of its destroyer, the merged mass cooling, and differentiating again into a slightly larger body, which was itself smashed into something larger, and so on, through millions of iterations, until all that material had been gathered into a single large body that we now call Earth. Every iron atom in your hemoglobin has been through this cycle. It has been part of a core, part of a mantle, part of a collision, part of a merger. It has been melted and solidified and melted again, passed from one embryonic world to another in a chain of destruction and creation that spanned millions of years and consumed thousands of small worlds. The chain extends further than most people realize. Before those iron atoms were in a protoplanetary core, they were in a molecular cloud, a cold, dark, tenuous fog of gas and dust drifting between the stars. Before that, they were in the interior of a massive star, fused into existence by the crushing pressures and temperatures at the stellar core. Iron is the end of the line for stellar fusion, the heaviest element that a star can build by combining lighter nuclei without consuming more energy than it releases. Every element heavier than iron, from cobalt to uranium, was forged in the cataclysmic explosion of a supernova when the outrushing shock wave compressed and heated material beyond the temperatures achievable in any star's normal burning. The iron in your blood therefore marks a boundary. The boundary between what stars can build during their lives and what can only be created in their deaths. You carry that boundary inside you, dissolved in your bloodstream, circulating through your veins, performing the humble biological task of carrying oxygen from your lungs to your tissues. Vesta is the one that escaped this chain. The one embryonic world that was not consumed, not destroyed, not absorbed into a larger body. It sits in the asteroid belt like a survivor at the edge of a battlefield, carrying within it the memory of what was lost. And what was lost was not just material. What was lost was an entire generation of small worlds, each one differentiated, each one carrying its own iron core and its own geological history, each one unique and irreplaceable. They are all gone now, folded into the interiors of the terrestrial planets, their individual identities erased forever. Vesta is the only one left to tell the story. There is a phrase that scientists sometimes use when they speak about Vesta in private, away from the formal language of journal articles and conference presentations. They call it a fossil planet, not a dead planet or a failed planet. Those terms imply something went wrong. Nothing went wrong with Vesta. It did exactly what it was supposed to do. It formed, it melted, it differentiated. It built itself a core and a mantle and a crust, following the planetary playbook step by step. The only thing it did not do was grow, and that was not its fault. That was Jupiter's doing. The gas giant's immense gravity stirred the asteroid belt into such a frenzy of high-velocity collisions that accretion became impossible. Instead of gently merging and growing, the planetesimals in the belt smashed each other apart, grinding potential planets into rubble. Vesta was large enough and structurally resilient enough to survive this grinding. But it could not grow. It was trapped, a planet in embryo, permanently arrested, frozen at a stage of development that every other terrestrial world passed through and left behind billions of years ago. Calling Vesta a fossil planet captures something important. A fossil is not a failure. It is a preservation. A fossil preserves the form and structure of something that no longer exists in its living state, a creature, an ecosystem, a moment in time. Vesta preserves the form and structure of a stage of planetary development that no longer exists in the solar system, the embryonic stage, the stage where a small world has melted and differentiated but not yet grown to full size. Every terrestrial planet passed through this stage. None of them preserved it. Vesta did. The analogy to biological fossils is, on reflection, remarkably apt. A paleontologist who discovers a well-preserved fossil of a Jurassic creature does not lament that the creature died. The death is what made preservation possible. A living creature continues to change, to grow, to adapt. Its body is a dynamic, evolving system that overwrites its own history as it develops. Only in death does the form become fixed, the structure stabilized, the record locked in place. The same is true of planetary bodies. Earth is a living planet. Its surface is constantly being reworked by plate tectonics, by erosion, by volcanic activity. The geological record of Earth's earliest history has been almost entirely destroyed by 4.5 billion years of geological recycling. Earth's oldest surviving surface rocks are roughly 4 billion years old, and even those have been heated, compressed, deformed, and chemically altered beyond easy interpretation. The first 500 million years of Earth's history, the period when the planet was accreting, melting, differentiating, forming its core, developing its earliest crust, is essentially a blank page. We call it the Hadean, after Hades, the Greek underworld, partly because conditions were hellish, and partly because so little evidence survives that the era might as well be buried in the underworld. Vesta fills that blank page, its death as a growing planet, its arrest at the embryonic stage, frozen in place by Jupiter's gravitational interference, is precisely what makes it invaluable, because it stopped changing. It preserved the record of what it was in those earliest moments. Its rocks crystallized and then stayed crystallized, undisturbed by plate tectonics that Vesta is too small to sustain, uneroded by weather on a world with no atmosphere, unrecycled by volcanoes that went extinct billions of years ago. The record is not perfect. Impacts have churned and mixed the surface, and some information has been lost to the relentless attrition of cosmic bombardment. But the fundamental structure is intact. The core is still there. The mantle is still there. The crustal basalts are still there. And the isotopic clocks in those rocks are still readable, still ticking, still carrying the timestamp of the solar system's earliest moments. And what it preserved is not just structure, it is time. The minerals in Vesta's rocks crystallized 4.5 billion years ago. The isotopic ratios in those minerals record the composition of the solar nebula at the moment of Vesta's formation, the decay products of short-lived radioactive elements, not just aluminum-26 but also iron-60, manganese-53 and others, provide a precise chronometer, a clock that has been ticking since the solar system's first moments. By reading these isotopic clocks in head meteorites, scientists have determined that Vesta completed its differentiation within the first 1 to 3 million years after the solar system began to form. It is one of the most precisely dated objects in the entire solar system, more precisely dated than Earth, which has been so thoroughly recycled by plate tectonics and erosion that its oldest rocks are less than 4.4 billion years old. Vesta is a better clock than our own planet. Now zoom out even further. Vesta is one world in one solar system orbiting one star in one galaxy containing roughly 400 billion stars. Our Milky Way galaxy is one of an estimated 2 trillion galaxies in the observable universe. Each of those galaxies presumably contains billions of stars, many with their own planetary systems, many of those systems presumably containing their own asteroid belts, their own protoplanetary remnants, their own versions of Vesta. The process that built Vesta, accretion, melting, differentiation, interrupted growth, is not unique to our solar system. It is a universal process, governed by the same physics everywhere in the cosmos. Wherever a young star forms from a collapsing cloud of gas and dust, wherever planetesimals begin to merge and grow, wherever a large planet forms early and gravitationally disrupts its neighbours, there will be Vestas. small, scarred, frozen embryos of worlds that never were, carrying the chemical memory of their star system's birth. This is not speculation. The evidence for rocky exoplanets, planets orbiting stars other than our Sun, has grown from a trickle to a flood in the past 2 decades. The Kepler and TESS space telescopes have identified thousands of rocky planets in other solar systems, many of them orbiting in the habitable zones of their parent stars, where liquid water could theoretically exist on the surface. If those planets are anything like Earth, and the evidence increasingly suggests that rocky planets form by the same accretionary process everywhere in the galaxy, then they were built from the same kind of Vesta-like embryos that built our planet. Their iron cores were assembled from the merged cores of countless small differentiated bodies. Their mantles and crusts were forged in the fires of collision after collision. And in every one of those distant solar systems, there were probably embryos that survived, Vestas of other suns, orbiting in other asteroid belts, carrying the timestamps of their own solar system's births in the isotopic chemistry of their ancient rocks. We will almost certainly never visit those distant Vestas. The nearest star is over 4 light-years away, roughly 25 trillion miles, and no technology in existence or seriously proposed can bridge that distance in a human lifetime. But we can study them indirectly. By understanding our own Vesta in exquisite detail, its formation timeline, its internal structure, its chemical evolution, its response to catastrophic impacts, we build a template that can be applied to every rocky planetary system in the universe. Vesta is not just a local curiosity, it is a Rosetta Stone for planetary formation, a key that unlocks the early history of worlds we will never see. We are, in a sense, surrounded by ghosts. The iron in our blood, the silicon in our rocks, the calcium in our bones. All of it passed through bodies like Vesta before arriving in Earth. Those bodies are gone now, consumed, absorbed, destroyed by the very process that created us. But one survived. One single, battered, cratered, troughed and scarred world managed to endure 4.5 billion years of bombardment, hold its iron core together, keep its layered structure intact, and arrive in the 21st century, carrying a message from the solar system's deepest past. Think about what it means to hold a eucrite meteorite in your hands. You are holding a piece of solidified lava from a world that completed its geological activity before Earth existed. The atoms in that rock were assembled in the interiors of stars that died before our Sun was born. They were scattered into space by supernova explosions, incorporated into the collapsing cloud that became the solar nebula, accreted into a planetesimal, heated by the decay of aluminum-26 that was itself born in a dying star, melted, differentiated, erupted onto Vesta's surface as lava, cooled, solidified, sat undisturbed for billions of years, were blasted off Vesta's surface by a catastrophic impact roughly 1 billion years ago, orbited the Sun as an independent object for hundreds of millions of years, crossed paths with Earth, entered the atmosphere at cosmic velocity, survived the heat and pressure of atmospheric entry, struck the ground, lay unnoticed for thousands of years, and were eventually picked up by a human being who had no idea what she was holding until she carried it to a laboratory and measured its isotopic composition. That chain of events is not metaphorical, it is literal. It is the actual physical sequence of events that connects a laboratory on Earth to a supernova explosion that happened before our solar system existed. And Vesta is the node in that chain, the way station, the archive, the messenger that makes the connection traceable. This is not science fiction. This is the reality we inhabit. And the reality is this. We live on a world that was built from the wreckage of 1,000 Vestas. And the only reason we know what those lost worlds were like is because one of them, one single, stubborn, impossibly resilient protoplanet, refused to be destroyed. Step back for a moment, take a breath, let the weight of everything settle. We began this journey with a simple image, a scarred, battered rock drifting in the darkness between Mars and Jupiter. A world so small you could drive across it in an afternoon. A name that most people have never heard. And now, having travelled through 4.5 billion years of history, through supernova shockwaves and collapsing Gapsard clouds, through melting interiors and catastrophic impacts, through decades of painstaking scientific detective work, and the audacious flight of an ion-powered spacecraft, we can see Vesta for what it truly is. Not an asteroid, not a curiosity, not a footnote in the solar system story. Vesta is the story. Or rather, it is the earliest surviving chapter of the story. The chapter that explains how everything we know came to be. The implications of what Vesta teaches us ripple outward in every direction, backward in time to the solar system's formation, forward in time to humanity's future, and outward in space to every planetary system in the galaxy. Consider first what Vesta reveals about the birth of Earth. For decades, our understanding of planetary formation was built on theoretical models and computer simulations. Abstract calculations that described how dust becomes pebbles, how pebbles become boulders, how boulders become planets. These models were powerful but untested. We could not observe the process directly. It happened 4.5 billion years ago, and the evidence had been erased by the very process we were trying to understand. The terrestrial planets are finished products. They bear the scars of their formation, but the intermediate stages, the embryonic worlds, the half-built planets, the molten protoplanets, in the process of differentiating, had been consumed. We were trying to reconstruct a recipe from a finished cake, without ever seeing the raw ingredients. Vesta changes that. Vesta is one of the raw ingredients. It is a planetary embryo, preserved in its incomplete state, available for study. By analysing Vesta's chemistry, its internal structure, its thermal history, and its impact record, scientists can test their models of planetary formation against a real physical example. Does the timing of Vesta's differentiation match what models predict? Do the proportions of its core, mantle, and crust align with theoretical calculations? Does the chemical composition of its rocks reflect the expected conditions in the solar nebula at its formation distance from the Sun? In every case, the answer has been yes, but with nuances and surprises that have refined and improved the models. Vesta has served as a reality check for planetary science, a benchmark against which theoretical predictions can be measured. And Vesta is not just a benchmark for our solar system, it is a benchmark for every solar system. The laws of physics are universal. Gravity, thermodynamics, nuclear decay. They work the same way in every galaxy, around every star, in every protoplanetary disk. If Vesta-like bodies formed in our solar system, they almost certainly formed in others. And if the process of planetary formation works the way Vesta's example suggests, rapid accretion, early melting driven by short-lived radioactive isotopes, differentiation into core mantle crust structures, then this process is likely universal. Every rocky planet in the galaxy probably passed through a Vesta stage. Every Earth-like world was once a collection of molten embryos, crashing and merging in a violent dance of construction. Vesta is not just our solar system's fossil, it is a template for understanding rocky planet formation everywhere in the universe. But Vesta also carries a warning. Its story is, at its core, a story about the precariousness of existence. Vesta survived, but barely. 2 catastrophic impacts nearly destroyed it. Jupiter's gravitational influence prevented it from ever reaching its potential. The asteroid belt that surrounds it is a killing field, littered with the fragments of bodies that were not as lucky, not as structurally resilient, not as well anchored by a dense iron core. For every Vesta that survived, there were probably hundreds of similar bodies that did not. They were shattered, ground down, scattered, and erased from the solar system's census. Their materials were eventually folded into the planets or ejected into interstellar space, and today there is no trace of them beyond the statistical models that predict their former existence. This precariousness extends to Earth. Our planet exists because the right number of embryos collided in the right sequence with the right energies over the right timescales. Change any of those variables, make the collisions slightly more violent or slightly less frequent, or shift the timing by a few million years, and the result might have been very different. A smaller Earth, a larger Mars, no Earth at all. The formation of a habitable planet is not an inevitable outcome of the physics. It is a contingent outcome, dependent on initial conditions and chance events that could easily have gone differently. Vesta reminds us of this contingency. It is the road not taken, the planet that almost was, and its existence is a quiet reminder that the outcome we enjoy the world we inhabit, was never guaranteed. There is also the question of what Vesta means for humanity's future. The asteroid belt, long dismissed as a region of scientific interest but little practical value, has in recent years attracted the attention of space agencies, commercial companies, and policymakers interested in space resources. Asteroids contain metals, minerals, and in some cases water, resources that could potentially be extracted and used to support space exploration, orbital construction, and deep space missions. Vesta, as a differentiated body with an iron core and a mineral-rich surface, represents a concentrated deposit of materials that could, in principle, be accessed far more easily than Earth's deep interior, where similar materials are buried beneath thousands of miles of rock. This is speculative, of course. No technology currently exists to mine an asteroid the size of Vesta, and the economics of space mining remain unproven, but the physical inventory is clear. Vesta's iron core alone contains more iron than humanity has ever mined in its entire history, by a factor of millions. Its surface basalt contains titanium, magnesium, calcium, and other elements useful in construction and manufacturing. The water delivered to its surface by carbonaceous impactors, while present only in trace amounts, could in principle be extracted and used as propellant or life support for crewed missions deeper into the solar system. The deeper point is not about mining, it is about perspective. For all of human history, we have lived on one world, surrounded by a sky full of points of light that seemed impossibly distant and profoundly irrelevant to our daily lives. Vesta challenges that perception. It tells us that the solar system is not a collection of distant, unrelated objects. It is a family, a connected system of bodies that share a common origin, a common chemistry, and a common history of formation and destruction. The iron in Vesta's core and the iron in your blood came from the same source, the nuclear furnaces of dying stars billions of years ago. The basalt on Vesta's surface formed from the same kinds of magma that built Earth's ocean floors. We are connected to Vesta not just by proximity or scientific interest, but by origin, by chemistry, by the fundamental processes that built everything we know. And then there is the most haunting implication of all. Vesta has survived for 4.5 billion years. It has endured everything the solar system has thrown at it. Gravitational disruption, catastrophic impacts, the relentless grind of cosmic bombardment, and it is still there, intact, persistent, enduring. Humanity, by contrast, has existed for roughly 300,000 years. Our civilization, the culture that builds telescopes and spacecraft and reads the chemistry of distant worlds, has existed for perhaps 10,000 years. The span of human existence is to Vesta's lifetime as a single heartbeat is to a human life. We are newcomers, beginners, temporary visitors in a solar system that has been conducting its business for longer than we can comprehend. Vesta does not care about us. It has no awareness, no purpose, no meaning beyond the meaning we project onto it. But in studying it, we learn something about the nature of persistence, about what it takes to endure, about the qualities, structural integrity, internal coherence, the ability to absorb catastrophic blows without losing cohesion, that allow a body to survive across geological time. These are not bad qualities for a civilization to consider cultivating. The universe is not gentle. It does not make allowances for fragility. The bodies that survive are the ones that are built to withstand what comes. Vesta was built that way. By accident, by physics, by the blind workings of gravity and radioactive decay and the orbital mechanics of a young solar system. No intelligence designed it, no consciousness intended it, and yet it endured. It is still out there, right now, orbiting the Sun in the cold darkness between Mars and Jupiter, carrying its iron core and its basaltic crust and its layers of impact scars through another orbit, another year, another epoch. It has been doing this since before Earth existed. It will likely continue doing it long after Earth is gone, swallowed by the expanding Sun in roughly 5 billion years, or scattered by some future gravitational perturbation, or left to drift in the darkness after the Sun itself has died and cooled to a white dwarf. There is something both comforting and terrifying about that thought. Comforting because it means that the record of our solar system's formation, the story encoded in Vesta's rocks, will likely outlast everything humans have ever built. Terrifying because it means that the universe measures time on scales so vast that even 4.5 billion years of survival is, from a cosmic perspective, only a beginning. So here we are, at the end of a journey that began with a question: how did a tiny, battered world in the asteroid belt manage to survive 4.5 billion years of cosmic violence? And arrived at an answer that is far larger than the question itself. Vesta survived because it was built like a planet. Its iron core, forged in the first few million years of the solar system's existence from the heat of a dying isotope, gave it structural integrity that no undifferentiated body could match. Its layered interior, core, mantle, crust, distributed and dissipated the energy of even the most catastrophic impacts, allowing the body to deform and scar without shattering. Its early and complete differentiation, powered by the ghost heat of aluminum-26, transformed a random aggregate of primordial dust into a coherent, resilient, planet-like structure that could absorb blows that would have destroyed anything less organized. That is the direct answer. But the deeper answer is more unsettling and more beautiful. Vesta survived because the universe builds things that endure, not intentionally, not with purpose, but through the blind, patient workings of physics. Gravity pulling matter together, heat separating it into layers, structure emerging from chaos. The universe creates objects that persist across timescales that dwarf human comprehension. Vesta is one such object. It has no consciousness, no will, no desire to survive. And yet it has outlasted everything that was alive when it formed. Every organism, every ecosystem, every species that has ever existed on Earth, by a margin so vast it makes the concept of longevity meaningless. Think about this. 4.5 billion years ago, when Vesta's interior was still cooling from its initial melting, Earth did not exist, not in any recognizable form. Our planet was a swarm of colliding fragments, a cloud of debris in the process of merging into something larger. The moon had not yet formed, the oceans had not appeared, life had not begun, the continents had not assembled, dinosaurs were unimaginable. They would not appear for another 4 billion years. Humans were so far in the future that the very concept of the future had no meaning. And Vesta was already there, already differentiated, already cooling, already carrying its iron core through the darkness of the asteroid belt, orbiting the sun in silence, waiting, not consciously, not intentionally, but with the patience of stone and metal, for someone or something to look up and notice it. Heinrich Olbers noticed it in 1807. Thomas McCord connected it to its meteorites in the early 1970s. The Dawn spacecraft orbited it in 2011, and now tonight you know its story. The story of a world that began the journey toward becoming a planet, was stopped by the gravitational tyranny of Jupiter, endured 2 impacts that should have killed it, lost pieces of itself that rained down on a world it would never visit, and survived, through sheer structural resilience, to become the oldest intact differentiated body we have ever studied. If the sun were the size of a basketball, Vesta would be a mote of dust too small to see without a microscope. It would orbit in the dim space between a pea-sized Earth and a marble-sized Jupiter, invisible, overlooked, easy to dismiss, and inside that invisible speck, an iron core, a layered interior, mountains taller than Everest, canyons deeper than anything on Earth, a billion-year-old impact scar that covers half the world, and the chemical signature of a supernova that exploded before our star was born, all of it packed into a body you could drive across in an afternoon. The question we asked at the beginning was how this world survived. But perhaps the more important question is what its survival means. And what it means, stripped of jargon and technicality, is this: the solar system remembers. It remembers its own birth, not in the way that conscious beings remember, but in the way that rocks remember. Through structure, through chemistry, through the arrangement of atoms that was determined billions of years ago, and has remained unchanged ever since. Vesta is one of those memories, a physical memory of the solar system's most violent and creative epoch, preserved in iron and basalt and the patient silence of 4.5 billion years of orbit. We are temporary. Our lives are measured in decades. Our civilizations are measured in millennia. Our species, if we are lucky, may be measured in millions of years. But Vesta has already endured for billions. It was here before us. It will be here after us. And in its silent, scarred persistence, it carries a truth that is both humbling and strangely reassuring, that the universe, for all its violence, is capable of preserving things. Not perfectly, not forever, but across spans of time so vast that even the word ancient loses its meaning. Right now, as these words reach your ears, Vesta is out there. It is orbiting the Sun at an average distance of 2.4 astronomical units, traveling at roughly 12 miles per second, completing one full orbit every 3.63 years. Its iron core sits at its center, dense and cold, surrounded by a mantle of olivine-bearing rock, capped by a battered crust of volcanic basalt. The Ria Silvia Basin yawns across its southern hemisphere. 310 miles of exposed geological history, a window into the interior of a world that began its story before ours had a chance to start. The equatorial troughs, Divalia Fossa and its companions, encircle the waste of the protoplanet like scars from a wound that healed but never faded. Dark patches of carbonaceous material dot the surface, souvenirs from ancient collisions with visitors from the outer solar system. And the central peak of Rhea Silvia rises 14 miles above the basin floor, a mountain that has stood unchanged for 1 billion years. No one is there to see it. No telescope is currently trained on it. No spacecraft orbits it. Dawn left Vesta more than a decade ago and has since exhausted its fuel, drifting silently in orbit around Ceres, its mission complete, its instruments dark. Vesta is alone again, as it has been for nearly all of its existence. Alone in the cold, alone in the dark, carrying its secrets through another orbit, another year, another age. But we know it is there. We know what it is. We know what it has endured. And we know what it means. It means that 4.5 billion years ago, in the violent, chaotic infancy of our solar system, a small world melted, organized itself into layers, and began the process of becoming a planet. It was stopped before it could finish. It was battered, scarred, and partially dismembered by impacts that would have destroyed almost anything else. It lost pieces of itself that travelled hundreds of millions of miles, and landed on a world that did not yet exist when Vesta was born. And yet it persisted. Through all of it, through the chaos and the violence and the immense grinding patience of geological time, it persisted. Vesta is the most violent world nobody talks about. And perhaps after tonight that will change. The universe is old, the universe is vast, the universe is violent beyond description. And somewhere in the middle of it, in the cold silence between two planets, orbiting a star that will one day die, there is a 326-mile-wide testament to the power of structure, the stubbornness of matter, and the extraordinary capacity of the cosmos to build things that last. It has been there since the beginning, and it is there still.